All right, welcome back to Inorganic TUTOR'S Institute. In today's lecture, we are basically going to cover about 20 multiple problems in Advanced Calculus 2, basically the chapter 2, right? We are going to simplify the chapter 2. Okay, so my question is, have you ever wondered how to turn a curve into a calculation, or how to connect Green's theorem with a force field? Look no further. Here we are going to solve 20 mind-opening problems that will enhance your understanding for exams and to the world at large. All right, let's begin with the first problem where we are asked to find the divergence of a particular vector field. Okay, so this is the first problem. We are given this vector field, all right, and we want to find the divergence of this particular vector field. Okay, so recall that vector field, this divergence is giving us, divergence of a vector field is giving us f1i plus f2j plus f3k, right? We've remembered this. Okay, now don't forget that divergence is, so divergence is obtained as partial differential of the first component, right, with respect to x, plus partial differential of the second component with respect to y, plus partial differential of the third component with respect to z. Okay, so once we have this, the rest is to identify our components, right? And we know that from the vector field, we know that our f1 is going to be 0 because we don't have any I component here. Okay, our f2 will be equal to e to the x y sine z, right? And our f3 will be y tan inverse of x on z. Okay, so we have all the components, right? Now, let's take the partial differential of the vector field with respect to what? X, right? So we are going to begin with that with respect to x. And we know that our f1 here is 0. So partial differential of f1, which is 0, will be equal to 0. You know, differentiation of a vector, a constant is 0, right? So we have that. Then we move to the second component where we have partial differential of the second component with respect to y. Okay, so this is our second component, and we want to differentiate with respect to y. So meaning we are going to use the exponential function. So you know that if you want to differentiate an exponential function, you differentiate the function on the exponential function, then use the result to multiply the exponential function again, right? So we differentiate xy with respect to y, and we have x, right, times xy, then we maintain our sine z, right? Then, so once we are done with the second component, we come to the third component, right, which is y tan inverse of x over z. Okay, so we are going to differentiate that f3 with respect to z. So we're going to have d of y tan inverse of x on z, right? So we are differentiating this product function with respect to z. And we know that differential of tan inverse is 1 over the function, 1 over 1 plus the function inside the tan. So we know that differential of tan inverse is equal to 1 over 1 plus the function inside the tan inverse, right? Squared, right? Times differential of the function inside the tan inverse. So now you don't forget that we are differentiating with respect to z. So it's going to be negative x over z squared, right? Don't forget that there is a y, okay? So we come up here, we have y times negative x over z squared 1 plus x over z all squared, right? So we're going to say that this is equal to negative xy divided by z squared all into 1 plus x over z, right? So let's try to simplify this. We're going to have minus xy divided by z squared into 1 plus x squared over z squared, right? And this is equal to, when you simplify this, don't forget that this is 1 over 1, right? So when you find LCM for this, then you're going to have minus xy divided by z squared into z squared plus x squared all over z squared, right? So we're going to have minus xy divided by z squared into bracket z squared plus x squared. So x squared plus z squared divided by z squared, right? So this takes off this, and then we have minus x y divided by x squared plus z squared. Okay, so this is the simplification to the derivative of y tan inverse of x on z with respect to z. So that is what we have. Okay, so now we've differentiated with respect to x of the first component, with respect to y of the second component, of which we had this, and then with respect to z of the third component, and we had this. So now let's combine all terms. So we're going to have this x e to the xy sine z minus this, right? xy divided by x squared plus z squared. So this is our solution to this particular problem. But this solution can be expressed as, this we have here can be expressed as x e to the xy sine z. This particular one can be expressed as x e to the xy tan z divided by square root of 1 plus tan squared z, right? So we can also express the first term as that. Okay, so we come up here. We know that x e to the xy tan z divided by square root of 1 plus tan squared z. Don't forget that tan is sine over cos. All right. And don't forget also that there is an identity that 1 plus tan squared z is equal to sec squared z, right? So if we need 1 plus tan squared z, then it means we can substitute sec squared z in place of this, right? So it means that the whole of this expression becomes square root of sec squared z, right? So that is equal to sec z, because this will take off this, right? So the denominator now reduces to sec z, all right? And we also know that tan z is sine over cos, okay? Don't also forget that sec z is 1 over cos z, right? So we're going to do that substitution here. So we have x e to the xy, and our tan z is sine over cos. So we have sine z over cos z, right? So this, everything divides that. Then this we have here has been simplified to 1 over cos z. So we have this divided by 1 over cos z. And when you do this algebra well, you're going to have x e to the xy sine z divided by cos z times cos z over 1, right? So we're going to have this taking off this. So we have x e to the xy sine z, right? So we can see that the first term that we have here has been expressed in this. So that is the first term, right? So we're going to put that there. So we're going to say that we have x e to the xy sine z is equal to x e to the xy tan z divided by square root of 1 plus tan squared z, right? So this is expressed as this, all right? So that is the first part. The second part is also expressed as negative xy divided by x squared plus z squared has also been expressed as minus y over x plus z divided by x plus z divided by square root of x all squared. All right, so this expression has been expressed in this form. So let's come up here. So we're going to simplify this expression. We're going to simplify this expression to see if it is the same as this, right? So we know that minus y over x plus z over square root of x all squared is equal to, now let's simplify this expression. So we have minus y divided by x plus this is square z squared, right? So we're going to have z squared over square root of x all squared, right? And that is equal to minus y divided by x plus z squared over x. Okay, so this is the same as minus y divided by this is over 1, right? So it means that when you find the LCM, we're going to have x squared plus z squared divided by x, all right? And this is the same as minus y over x squared plus z squared times x over 1, right? You know that if you have a over b over c, it's the same as a times C over B, right? We are applying that knowledge here. So we're going to have minus xy divided by z squared plus s squared. And that is basically this. So this expression has been expressed in this form. So we can conclude that our divergence of the vector field f is equal to minus y divided by x plus z all over square root of x all squared plus x e to the xy tan z divided by square root of 1 plus tan squared z, right? Or yet we can bring this and bring this here, right? So we have x e to the xy tan z divided by square root of 1 plus tan squared z minus y over x plus z over square root of x all squared. All right, so this becomes our divergence to this particular vector field. On the question paper is option number C. So this is our final answer to question number 1. So this is the process that we go through to find divergence of a particular vector field. First of all, identify the components, each component. Then don't forget that to find the divergence of a particular vector field, you differentiate the first component with respect to x partially, right? Then differentiate the second component with respect to y partially, and then the third component with respect to z also partially. Once you are done, combine all the terms and you are good to go. Now let's move into this question number 2. Okay, so with problem number 2, we want to find the curl of this same vector field, right? At the point 0, 1, and pi on 4. All right, the same vector field that we used in problem number 1. All right, so don't forget, with curl, if you want to deal with curl, then you have to think about matrices, right? Don't forget that matrix order is very important in matrices, right? So in here, especially multiplication of matrix, right? So you know that curl is giving us I component, j component, and k component. Then we find partial of the first component with respect to x, partial of the second component with respect to y, partial of the third component with respect to z, right? So the first component here is 0. The second component here is e to the xy sine z. And the third component is y tan inverse of x on z. Right, so this is what we are going to find the determinants. All right, so don't forget that if you are dealing with curl, then we are talking about matrices, and multiplication of matrices is not commutative. It's not commutative at all. So you have to be very careful dealing with this. So we are going to find the determinants. Then when we are done, we evaluate it at this point. Okay, so we begin. When you stand on the first row, then it means that any other element, when you are taking the first element on the first row, any other element on the below the first element on the first row will be ignored. Then any other element on the first row will also be ignored. So we're going to have this alone. So we're going to have this with respect to y, this with respect to z. Then we have e to the xy sine z. Then we have y tan inverse of x on z. Right? Then we come to minus j into, when you take this, then you avoid any element below it, any element on the row. So we're going to have this with respect to x, 0. Then with respect to z, y tan inverse of x on z, right? Plus k into, when you take this, any other element under it will go off. Here will go off. So we're going to have with respect to x, 0. With respect to y, e to the xy sine z. All right. So now that we have been able to decompose our 2 by 2 matrix from the 3 by 3, then let's find the determinant, right? So we're going to have minus, we're going to have I into this to this, right? So we have partial differential of y tan inverse of x on z with respect to y, right? Minus d of e to the xy sine z with respect to z. Then minus j into this, right? d of y tan inverse of x on z with respect to x, right? Minus this with respect to z of 0. Then we come to this, the k component, plus k into d of e to the xy sine z with respect to x minus with respect to y of 0. All right, so this is what we have so far. So we come here, we have I into, we differentiate y tan inverse of x on z with respect to y. So it means that we are only going to differentiate y. The rest, tan inverse of x on z, has nothing to talk about, say y. So we only talk about the y here. So don't forget, we are going to use the product rule. So it means that we differentiate y and we maintain tan inverse of x on z. Then we come to this, we differentiate tan inverse of x on z with respect to y, of which is going to be 0. So we're going to have that to be 0 minus e to the xy sine z with respect to z. So it means that we are going to handle the sine z. So when you differentiate sine z with respect to z, you're going to have cos z. Then we maintain our e to the x, y. That. Okay. So that is that for that portion. Okay. We come to the j components. We differentiate y tan inverse of x on z with respect to x. So it means that we are going to have y times 1 on z, y times 1 on 1 plus x on z all squared times, we differentiate x on z, and that is going to be 1 on z, right? Then minus, we differentiate 0 with respect to z, that is 0, right? We come to the k component. We differentiate e to the xy with respect to x, right? So we're going to have y e to the xy, then we maintain sine z, right? So that is it for that portion, minus 0, right? So we are going to simplify that. So, when you simplify tan inverse of x on z, then that portion is going to be tan inverse of x on z minus e to the xy cos z, or I. Then we come to the j component. We're going to have y divided by z into 1 plus x squared over z squared, right? That's minus or g. Then we come to the k component plus y e to the xy sine z, or k, right? So now we come up here. So we're going to have this tan inverse of x on z minus e to the xy cos z, or I, then negative y divided by z into x squared plus z squared divided by z squared, right? Or g plus y e to the xy sine z, or k, right? So now we can start to substitute our points. We can evaluate it at this point. So we know that this can further be simplified to tan inverse of x on z minus e to the xy cos z, or I, plus minus y over, this will take one of this, so we're going to have x squared plus z squared divided by z, or j, plus y e to the xy sine z, or k, right? So now let's evaluate it at the point. Let's evaluate it at the point. So at x equals 0, y equals 1, and z equals pi on 4, we are going to have, we're going to substitute that inside. So that will be tan inverse of x is 0 and z is pi on 4 minus e to the 0 into 1 cos into pi on 4, or I, plus y is 1, so it's going to be minus 1 over 0 squared plus pi over 4 all squared divided by pi over 4 all g, plus 1 e to the 0 into 1 sine into pi on 4, right? Okay. So don't forget that this is 0 over pi on 4, so that is going to be 0. Okay, so when you simplify all this, you're going to have minus square root on 2 or I minus this, this we are supposed to reciprocate it, right? So that we have pi on 4 divided by pi squared over 16, right? So this is all G, right? Plus this portion as well becomes square root of 2 or K, right? And this can be simplified to minus square root of 2 or I minus 4 on pi j plus square root of 2 over 2 or k, right? If you simplify this here, this will cancel one of this, then you're going to have minus pi on 4 on pi. So that becomes our final answer to the problem. This can also be expressed as minus 2 over 2 square root of 2 or I minus 4 on pi j plus 1 on square root of 2 or k, right? So eventually, when you cancel out, you come back to this. I rationalize this straightforward, but this, if you don't rationalize it, you have this. So this is the same as this. All right, so we can as well, so that becomes our curl of this vector field at this point. So that is question number 2. So basically, if you want to find curl, you have to know that you are going to deal with matrices, and in dealing with matrices you have to be very careful, right? And multiplication of matrices is not commutative, so you have to be careful with how you arrange the terms. All right, so let's move on to question number 3. Okay, so that is the final solution to question number 2. Minus 1 over square root of 2 minus 4 on pi, and then 1 over square root of 2. So that is the angle bracket form, and this is the position vector form, right? Okay, so with question number 3, we want to find this constant alpha and beta that will make this vector field conservative. And we know that when we talk about conservative of a vector field, then we have to make sure that we have curl free, meaning when we find the curl, it should be equal to 0. So here, this is our vector field. So we are going to ensure that this vector field is curl free, right? So for that to happen, okay, let's first write P I Q J plus R K, right? So for this to be conservative, that means that when we find the curl, it should be equal to 0, right? So we are going to check that. So meaning that we have to find partial derivative of r with respect to y, and that should be equal to when we find the partial derivative of q with respect to z, right? So that is first equation. Then 2, when we find partial derivative of p with respect to z, it should be equal to when we find partial derivative of r with respect to x, right? So that is 2. And then 3, when we find partial derivative of q with respect to x, it should be equal to partial derivative of p with respect to y. So we are going to check if these conditions will work, then it means that this vector field is conservative, right? So let's begin. We are going to find partial derivative of r with respect to y. So let's identify our r. So from the vector field, we know that our p is alpha x ln x. Our q is beta y squared z. And our r is x squared over z plus y cubed, right? So we are going to begin with the first equation, right? So partial derivative of r with respect to y here. So we're going to have with respect to y, right? So with respect to y, meaning that the whole of this is going to 0, then we differentiate y cubed, we're going to have 3y squared, right? Then we come to this. When we differentiate q with respect to z, of which we have our q here to be beta y squared z is equal to, we are differentiating with respect to z, so we're going to have beta y squared. So we said that this should be equal to that. So we're going to have 3y squared equals beta y squared, right? So when we divide by y squared, we have this going off, this as well going off. So we're going to have beta to be 3, right? So we have the value of beta to be 3. So once we have that, then it means that we have to also come to this partial derivative of z with respect to p. So, right? So of p, so x, alpha x ln z, right? Alpha x ln z with respect to z. When you differentiate ln z, right? Alpha x ln z with respect to z, we're going to have 1 over z times differential of z is 1, right? Then we have our ax. So that is the first part. Then we come and consider partial differential of r with respect to x. So that will be partial differential of r with respect to x will be equal to, our r is x squared over z plus y cubed, right? So we are differentiating with respect to x. So we're going to have 2x over z, right? This is y cubed. So with respect to s, you're going to what? 0. So this is what we have. So we're going to equate this to that. So here we're going to have ax over z equals 2x over z. So that means that when we cross multiply, we're going to have 2xz equals axz. So we divide by ax, divide by ax. So this, no, we divide by xz. So this cancels this, and this as well cancels this. So we have our alpha to be 2. Right? So once we have alpha and beta, then we have satisfied the question. But the question says this vector field is conservative. So meaning that if we substitute alpha and beta, then this result, when you find curl of it, is going to be what? 0. That is the main motive. So in here, the question demanded the value of alpha and beta. So that's alpha is equal to 2 and beta is equal to 3. So that is question number 3. Now let's move on to question number 4. With question number 4, we are going to build on this problem. All right. With question number 4, we want to find the potential associated to F for which it is irrotational, right? This is the potential, the vector field. And from question 3, we know that our alpha is 2 and our beta is 3, right? So let's substitute into that to have our original potential, our original vector field. So we're going to have 2x in z I plus 3y squared z j plus x squared over z plus y cubed. Okay, right? So this question wants us to find the potential function, right? The potential function phi of x and y, phi of x, y, z, such that phi of f, such that this is equal to what? F, right? This question wants us to find the potential function such that the change of the phi is equal to what? F. That is the gradient, right? So now let's use this, right? We know that F is equal to what? Gradient times phi, right? And that is equal to partial derivative of phi with respect to x of the first term. So that is 2x ln z. And then partial with respect to y of phi equals what? 3y squared z, and partial of phi with respect to z equals x squared over z plus y cubed, right? So this is what we have, okay? So this function that we have, we want to find the potential function such that the gradient times phi is equal to what? The vector field. Now, in other words, this question wants us to find the reversing, right? We are reversing the gradient, right? We are trying to find the original function whose partial derivatives match the component of what? F, right? Whose partial derivative match the component of F. So what we are going to do right now is to take this, integrate with respect to each variable, then we take this, integrate with respect to each variable, then we take this, integrate with respect to each variable, then we combine it, and that becomes our potential that is associated to F, right? So we begin with this of phi equals 2x ln z, right? And we know that if you need phi here, that means you have to integrate both sides, right? So we integrate both sides with respect to x, right? So this goes here. We're going to have the phi of equals 2x ln z, right? So this takes of this, we have phi equals, when you integrate this with respect to x, then we're going to have 2x squared divided by 2 ln z plus, we integrated with respect to x, so the rest of the variables becomes our constant, right? So that's going to be h of y and z. So we say that our constant is h of y and z. From our pre-calculus, we were integrating with respect to only one variable, right? That is why whenever we integrate, we add a constant of integration. But once you have 2, 3 variables, when you integrate, the variable that you integrated with respect to will remain constant, then the rest, right? So we're going to have phi to be equal to x squared ln z plus h of y z, right? So this is what we have for the first component. So we come up to the second component, di phi over di y is equal to di of 3y squared z with respect to y. So this, we are going to integrate with respect to y. So this here, then this here, right? So this takes of this, we have phi equals, when integrate this with respect to y, we are going to have 3y cubed divided by 3 z plus our constant. This we integrated with respect to y, and it was involving y and z. So meaning our constant is going to be either j of z alone, right? Any this one that you use. So we're going to have j of z, right? So if you have x, y, z, and you integrate with respect to x, then your constant is going to be what? H of y and z. But if you have only y and z, and you integrate with respect to y, that means your constant is going to be what? H or j of what? Z, right? So that is how we do it. Now let's move on to the last part, where we integrate this with respect to z. That means that we're going to have phi equals 0 plus 0, right? Don't forget, this is the same as s squared z to the negative 1. So when you add here, the z will go towards 0. So this as well is 0. So that part goes to 0. So we're going to have our phi to be equal to 0. So now let's simplify this. We're going to have y cubed z plus j of what? Z. Now this becomes our potential function, x squared ln z plus h of y comma z, and y cubed z plus j of what? z. So we come here and we say that our phi of x, y, and z equals x squared ln x plus y cubed z plus a constant, right? Plus a constant, but but you can decide to leave the constants plus y cubed z. So this becomes our potential associated to F, for which it is what? Irrotational. So that is question number 4. On our options, that is option A. Option A. So that is the process we go through to find the potential associated to a particular vector field. Okay, now let's move on to question number 5. All right, so from question number 3 and 4, we've already verified that this vector field is conservative, and also it has a potential function, right? Of which we had the potential function to be phi of x, y, z to be equal to x squared ln x plus y cubed z plus c, right? So this is the potential function that we have. Now we want to compute this line integral if c is the path along which the field moves from the point 1, 1 to 2, 1, 2, right? So we know that if you want to evaluate this, then we know our formula to be f dot r equals the first this minus this, right? So we evaluate it at 2, 1, 2 minus the evaluated at 1, 1, 1, right? So we evaluate at this point and also we evaluate at this point. So this basically means that we evaluate 2, 1, 2. That means our x is equal to 2, our y is equal to 1, and our z is equal to 2. So we're going to substitute into this potential function. Then we know the value at that point. So we're going to have phi of x of 2, 1, 2 equals x is 2, so 2 squared, ln into z is 2 as well, plus y cubed, and our y is 1, so 1 cubed, z is also 2, so we have 2 here. So our phi of 2, 1, 2 is equal to 2 squared is 4 ln 2 plus 2, right? So this is what we have at this point, right? Now, at 1, 1, 1, we're going to have phi of 1, 1, 1 equals, we're going to substitute into this potential function. So we have 1 squared ln into 1 plus 1 cubed times 1 here. Then we're going to have 1 ln 1 plus 1. And we know that ln 1 is 0. So we're going to have 0 times 1 is 0. And so we have 0 plus 1, right? So at 1, 1, 1, we have 1, right? So this is what we have at 1, 1, 1. And this is what we have at 2, 1, 2. So now what we have to do is to subtract this from this, right? To get the f dot r at this point. Okay. Now the reason why I didn't bring the constant c is that when we subtract this from this, the constant will go away automatically, right? So we're going to have our line integral f dot r to be equal to 4 ln 2 plus 2 minus 1, right? So eventually we are going to have 4 ln 2 plus 2 minus 1 is basically 1. All right, so this is what we have at this point. So you're going to have 4 ln 2 plus 1. And this is equal to 3.77 here, right? So 4 ln 2 plus 1 is the same as 3.77. And that is option number C on the question paper, right? So that is option number C, option C. So that is question number 5. Okay, now let's move on to question number 6. With question number 6, we want to find the center of mass of the wire if the linear density at any point is proportional to its distance from the line, y equals 1. Now, they've hinted us that the center x bar y bar is equal to 1 over m, all multiplied by the integral of sp of x and y dx, comma, integral of yp x and y dx, right? So this is basically the moment at y, and also this is the moment at x. Now, this is how the question goes. A wire takes the shape of the semicircle. You know that semicircle is x squared plus y squared equals 1. This is basically at the origin, right? You know, at the origin, you have 0, 0 at the center, right? So x squared plus y squared is equal to 1, where y is greater than or equal to 0. Okay, and it takes its and is thicker near its base than near the top, right? And that is what we want to find the center of the mass. Okay, so first of all, let's do this analysis. We know that the wire shape is semicircle, so the wire's shape is semicircle, right? Which is x squared plus y squared equals 1, and y is greater than or equal to 0. Okay, and we also know that the linear density, right? The linear density P of x and y, P of x and y okay, so I'm naming the linear density at any point to be P of x and y. Okay, so the linear density at any point, I'm naming it P of x and y. So at P of x and y is proportional to its distance from the line y equals 1 from here. Okay, Now, the formula from the question, the formula for the center, of mass is x bar y bar equals 1 over m multiplied by integral of xp into xy dx, comma, integral of x yp into xy dx, right? Or in a big bracket. So you find the moment at y and the moment at x. When you are done, then you take the average, right? So the average is going to be this over m, this over m. Then you get for x bar and y bar, and that will be the center of the mass. All right, so let's begin with the process. So basically, we have to determine the linear density. We have to determine the linear density function, right? So we know that we need to determine the linear density function. So the next thing we have to do is to find the total mass, right? So step 1, we have to calculate the total mass m. Until we calculate the total mass m, we can't find the center or the average. Okay, so we have to calculate the total mass m. So this is how we are going to calculate the total mass m. So the total mass m will be equal to integral p of x and y dx, and that is equal to integral from 0 to pi of k into 1 minus sine t dt. We know that the question said the linear density P of x and y is proportional to its distance from the line. So it's proportional to its distance from the line, y equals 1, right? So that is where we got this right here. So we're going to say that m equals, we are going to integrate this particular function, right? We are going to integrate this. And from the question, okay, so let's integrate this, right? Let's try to integrate that. So we know that k is a constant, so we factor k out. Integral from 0 to pi of 1 minus sine t dt, right? So we're going to have k integral of 1 minus sine t is going to be t. When you integrate sine, it's going to be negative cos. So negative is going to be positive. So plus cos t, right? So this is the result of our integrand. Don't forget from 0 to pi. So we're going to have our total mass to be k into t is pi plus cos into pi minus 0 minus cos into 0, right? So this, we are going to have our total mass to be equal to k into, pi plus cos pi, right? Cos pi minus 0. Cos 0 is basically 1, so we have minus 1, right? So we have our total mass to be equal to k into pi minus 1, and cos pi is also minus 1. So we have minus 1, minus 1, right? So we're going to have our total mass to be k into pi minus 2, right? So it's basically telling us that our total mass, the total mass m, is equal to k into pi minus 2. So this is the m, the total mass m. So we're going to find the moment at y and the moment at x. When we are done, then we divide this by the total mass, right? So let's move here. So we calculate the moments at y, right? So we have my equals integral sp of xy dx, right? And we know that this is equal to 0 to pi cos t dot k, right? Cos t times k into 1 minus sine t, right? dt, right? So don't forget that the x comma y dx is basically the radius that we obtained, differential of the radius that we obtained as 1 minus sine t dt, right? So that is why we are using this. Okay, so we're going to have the moment at y to be equal to from 0 to pi cos, okay, let's integrate this straightforward. So when we integrate that, we can factor the k out because it's a constant. So k out, cos into 1 minus sine t dt, right? So we're going to have my equals k into, when we integrate cos, all right, cos t minus sine t cos t, right? So all dt. Okay, so we have our moment at y to be k into integral of cos is basically sine, right? So we have sine t, then integral of sine t cos t is half cos squared t, right? From 0 to pi. So our moment at y will be k into, let's substitute the limits inside. So we're going to have k into sine t is now going to be sine pi. So we have sine pi plus half cos into pi squared minus sine into 0 plus half cos into 0 all squared. So basically, we are going to have our moment at y to be equal to k into 0 plus half. You know, when you take sine of pi, you have 0. Then half of cos pi is basically 1, right? So we have half in there minus sine 0 is 0. Sine 0 is 0, and also cos 0 is basically 1. So 1 times half is half. So minus half. Okay. So we're going to have my to be equal to k into half minus half is basically 0, right? So we have our moment at y to be 0. Okay. So we have the moment at y to be 0, and we have our total moment, our total mass to be k into pi minus 2. So let's put that there. Our m is equal to k into pi minus 2, and our my is equal to 0, right? So we have to calculate the moment at x as well. So we calculate the moment at x, right? So this part. So we're going to have integral yp of x and y. Okay, so the moment at x, the moment as s, we know that this is the formula, right? So we're going to have our ms to be equal to integral of yp into x and y dx. And we know that our at any point xy dx is basically 1 minus sine t dt, right? So this here is this. And we know that our yp is equal to k times sine t, right? So we're going to have ms to be equal to integral k sine t into 1 minus sine t dt. So we have our ms to be equal to k is a constant, so k comes out, all right? And then from 0 to pi, sine t minus sine squared t, right? So we're going to have this dt, right? So we come here, we say that our moment at x will be equal to our k out. When we integrate sine, we're going to have negative cos t. And also, you know, this we have to apply. Okay, so this we have to apply the double integral here. So let's maintain the integration sign, the integrand, okay, minus cos sine squared t dt, right? Don't forget that from our double integrals, this is an identity. Sine squared t is equal to 1 minus cos 2t all over 2, right? So we substitute this in place of sine squared t, right? So we have our ms to be equal to k out from 0 to pi sine t minus into 1 minus cos 2t over 2 all dt. So we have our ms to be equal to k from 0 to pi sine t minus 1 plus cos 2t all over 2, right? dt, right? So this, we're going to have ms to be equal to k. We can factor so okay, so we can say that now that we have this, we can say that we have integral from 0 to pi sine t minus half plus cos 2t over 2 all dt, right? So now we can integrate this, and then we say that ms is equal to k into, when you integrate sine, you are going to have cos, right? Negative cos. So negative cos t, then when you integrate negative half, you have negative half t. Then we integrate cos 2t over 2, and that is plus 1 over 4 sine 2t, right? From 0 to pi. Don't forget, when you integrate cos 2t, you're going to have sine 2t over 2. And already there is a 2 there, so it's going to be what? 4. So that is why we have this. Okay, so we come up here. We say that our moment at x will be equal to k into negative cos t minus half plus sine 2t all over 4 from 0 to pi here. So now we can substitute the limit inside. So we have our ms to be equal to k into negative cos into pi minus half t. So our t here is pi plus sine into 2 pi over 4 minus cos into 0 minus half into 0 plus sine into 0 over 4, right? So eventually we are going to have k into cos pi is basically negative 1. So we have negative becomes positive, right? So we have positive 1, right? Then we have negative pi on 2, then sine 180 is basically 0. So we have plus 0, then minus cos 0 is 1. So we're going to have negative. It's going to be positive 1, right? Then we have 0 here, plus 0, then sine 0 is basically 0, right? So we have our ms to be equal to k into 1 plus 1 is 2, so we have 2 minus pi on 2. Right, so that is our ms, okay? That is our ms. So our moment at s is equal to k into 2 minus pi on 2, right? So now for us to get the center of mass, then the center of mass, that is x bar, y bar, will be equal to this. We take first take this this over this. So we're going to have 0, that is my over m, comma ms over m, right? So that is going to be 0 over m, which is k into pi minus 2, comma, our ms is k into 2 minus pi on 2, all over our m is also k into pi minus 2, right? So we're going to have our first part, s coordinate to be 0, then this k will take this k, then we're going to have 2 minus pi on 2 divided by pi on 2, right? So we're going to have our center of mass to be equal to 0, 0, 4 minus pi over 2 into pi minus 2, right? So when you evaluate this, we're going to have, when you evaluate this, we're going to have 0, this, when you evaluate this value, we're going to have 0.37597, right? So eventually our point is going to be 0 and 0.38. Okay, so this is our center of mass. So this becomes our center of mass to this particular problem. Okay, so basically this problem is very easy, but how you realize that it is proportional. Don't forget, if it is proportional, it means that there is a constant, right? So if you say P is proportional to Q, then if you introduce an equality sign, then you're going to have P equals what? KQ. So the same knowledge we apply in this problem to have our solution. 0, 0.38. So let me write the solution here boldly. So our center of, so the center of mass m of x, s bar y bar is equal to 0 and 0.38. Okay, so this is our center of mass to this particular wire. Okay. So that is the end of problem number 6. Don't forget, if you have a problem of this form, this is a practical problem, right? So you have to, you have to apply variation, right? Proportionality. You have to know that if you say something is proportional, then it means that it is, when you introduce an inequality sign between these two variables, then you're going to have KQ. That is directly proportional. But when we say indirectly proportional, then, or inversely proportional, that is going to be 1 over K over what? Q. Right? Though this is indirectly or inversely proportional, and this is directly proportional. In here, we are saying that it is proportional. Once it is proportional, it is directly proportional. All right, so let's move on to question number 7. Okay, so with question number 7, we want to evaluate the line integral x minus 2y, where c is the path from 0, 1, 0 to 0, 0, 1, 0, 0, 1 to negative 2, 0, 2, from negative 2, 0, 2 to negative 1, 1, 0, and finally from negative 1, 0 to 0, negative 1, 1 to 0, and to 0, 1, 0. Okay, so basically this question, what it requires of us is to basically parameterize each segment, right? And when we parameterize each segment, then evaluate it at this given line integral, right? So solution. This question, we are going to first, this is basically a scalar line integral. It is a scalar line integral, and for each, you know, these are segments. They are divided into segments or sections. So for each segment, we going to parameterize the path. Then B, we will evaluate f of x and y, which is equal to x minus 2y. Then C, we'll make sure that we compute arc lengths. We compute arc lengths. That is dx equals r prime of t dt. Then D, we'll find the, or we integrate f of x, y, dx, right? Where the x here is r prime of t dt. Okay, so we are going to deal with it segment by segment. So segment by segment, right? So first segment is from this 0, 1, 0 to 0, 0, 1. Okay, so from 0, 0, 0, 1, 0 to 0, 0, 1, right? So first of all, we see the statement here. This is what we are going to go through for each segment. So first, we're going to parameterize this, right? So when we parameterize that, we're going to have, so let's name that R1. Okay, so R1 of t will be equal to 0, 1 minus t, t, right? So this is our parameterized equation. So this becomes our vector field, right? So R1 is basically R of t equals 0, 1 minus t, t, right? So this is how we get that. You know that parameterized equation for the first segment, right? So this means that t belongs to 0 and positive 1, right? So then x equals 0, y equals 1 minus t, and z equals 0, right? Because we don't have any z here. Okay, let's forget about that. So x is 0, y equals 1 minus t. From the question, right? So we are using the function x minus 2y, right? So once we are done with the parameterization, we are going to evaluate at this point, right? So we're going to have x minus 2y to be equal to, our x is 0, so we have 0 minus 2 into 1 minus what? T. So we have x minus 2y to be equal to minus 2 plus 2t. Okay, so that is 2t minus what? 2. Okay, so once we have this, then we have to find the radius, right? We have to find the differential of the radius. So we're going to have r prime of t to be equal to r1 of t to be 0, 1 minus t, t, right? So we're going to find the differential of that, and that is going to give us 0, negative 1 and 1. All right, so we need the magnitude of that. So that will be equal to 0 squared plus negative 1 squared plus 1 squared, right? So 1 squared, negative 1 squared is 1 plus 1 squared. So it's going to be what? Square root of 2. So our r prime of t, r1 prime of t to be equal to square root of 2. So once we have the parameterized point and we've evaluated it at x minus 2y, of which we had minus 2 plus 2t, and also we've differentiated the parameterized equation, of which we have square root of 2, then we're going to say that our integration will be 0 to 1 of negative 2 plus 2t dt. So we're going to have integral of that, okay, square root of 2 dt. So we have this from 0, okay, this is a constant, right? Or, yeah, so let's try to open the brackets. So we're going to have minus 2 square root of 2 plus 2t square root of 2, right? Or dt, right? So we are integrating with respect to t. So this we are going to have, we can factor square root of t out, square root of 2 out. So we have 0, 1 of minus 2 plus 2t dt, right? So we are integrating with respect to t. So we have square root of 2, then we integrate minus 2 with respect to 2t. We're going to have minus 2t plus 2t squared over 2 from 0 to 1. So square root of 2 into minus 2t plus t squared from 0 to 1, right? So from here, we're going to say that square root of 2, we evaluate it at 0 to 1. So we're going to have minus 2 into 1 plus 1 squared minus into 0 plus 0 squared, right? So we have square root of 2 into minus 2 plus 1 minus 0. And this is basically square root of 2 into minus 2 plus 1, right? So we're going to have square root of 2 minus 2 square root of 2. Right? So our first segment is giving us square root of 2 minus 2 square root of 2. And this is basically equal to negative 1.414. So that is our first segment. So let's write that here, negative 1.414. Okay, so that is at the first segment from 010 to 001. Okay, so now let's move to the second segment. So segment 2 we have from 001 to negative 202, right? So we have to look at the process. We have to parameterize the part, right? So first of all, we will parameterize this to have R2 of t equals minus 2t, comma 0, comma 1 plus t, right? 1 plus t. So once we have the parameterized equation, the next thing we have to do is to evaluate f of xy, which is equal to x minus 2y. So b, x minus 2y, which will be equal to x here is minus 2 and 2y, y is 0. So it's going to be minus 2 into what? 0. So we have x minus 2y equals what? Minus 2. Right, so this is what we have for the second segment after evaluating. So we have to now compute the arc length, which is the x is equal to r prime of r2 prime of t dt, right? So we go here, we find r prime of r2 equals minus 2, 0, and 1, right? So we're going to have r2 prime of t, magnitude of that will be equal to square root of negative 2 squared plus 1 squared, and that is equal to square root of 5, right? So we have r2 prime of t, magnitude of that to be square root of 5. So once we have the arc length, then we can integrate f of x and y, right? So we're going to have minus 2t. Now the s is what? Square root of 5 dt, right? So we're going to have, when you integrate this, this is basically minus 2 square root of minus 2 integral of t square root of 5 dt. So we can still factor this out to have this t dt. Don't forget, this is also in the range of 0, and 1, right? T belongs to 0 and 1. So we're going to evaluate from 0 to 1. Okay. So let me clean up this part. So when we do that, from 0 to 1 of negative 2 square root of 5, from 0 to 1 of t dt. So we're going to have minus 2 square root of 5. When you integrate t, you're going to have t squared over 2 from 0 to 1. So we have minus 2 square root of 5, 1 over 2 minus 0, right? So we're going to have minus 2 square root of 5 over 2, and that is equal to minus square root of 5. Okay, so this is basically equal to minus square root of 5 is basically equal to negative 2.236, right? So this is what we have for the second segment. Okay, so let's put that here, minus 2.236. Okay, so we evaluate for the third segment. We are following the same process. So third segment from negative 2, 0, 2 to negative 1, 1, 0. So we parameterize that. We're going to parameterize that part to have R3 of 2 equals negative 2 plus t, negative 2 plus t, comma, t. Then we have 2 minus 2t, 2 minus 2t. Okay, so this as well, t belongs to 0 and 1. Okay, so our x minus 2y, of which we are evaluating at, x is minus 2 plus t, and minus 2 into y is t, right? So we have s minus 2y equals minus 2 plus t minus 2t, right? So we're going to have t minus 4t. Okay, so this is minus 2t minus 2, then t minus 2t becomes minus t. So we have minus 2 minus t. So now that we have the evaluated points, let's find the arc length. So we know that the x is equal to R3 prime of t, magnitude of that the t. So we find R3 prime of t, and that will be equal to, we differentiate this with respect to t, you're going to have 1. Then with respect to t, we have 1. With respect to t, we have minus 2, right? So magnitude of this will be equal to square root of 1 squared plus 1 squared plus negative 2 squared. So that will be 1 plus 1 plus 4. And that is square root of 2 plus 4, which is square root of 6. Right. So we have that to be square root of 6. And we have our computed or evaluated point at x minus 2y to be, so we're going to have 0 to 1 of negative of negative 2 minus t, right? And our ds is square root of 6 dt. So we're going to have square root of 6 from 0 to 1 of -2, -t. So when you integrate this, you're going to have square root of 6, -2t minus t squared over 2, 0 to 1. Then we have this here, we're going to have -2 minus 1 on 2, right? When you put 0 inside, that part will go. So we're going to have square root of 6 into -5 on 2. -2 minus half is -5 on 2. So basically, we are going to have -5 square root of 6 on 2, and that is equal to -2.5 square root of 6, right? And this is basically equal to, it's approximately equal to -6.124. Okay, so the third segment, it gave us -6.124. All right, so we have to look at the fourth segment. The fourth segment, 3, 4. So the fourth segment, is going to be from -1, 1, 0 to 0, 1, 1. 0, 1, 0, right? 0, 1, 0. Okay, so first of all, we parameterize this. So when you parameterize that, so that is going to be R4 of t, and that is going to be -1 plus t, -1 plus t, 1, then we're going to have 0. So R4 of t is equal to -1 plus t, 1, and 0. Okay. So this is what we have. So now we have to evaluate f of x, y equals x minus 2y. So f of x, y equals x minus 2y equals, our x is -1 plus t. So we have -1 plus t minus 2 into 1. So we have -1 plus t minus 2 minus 3 plus t. So this is what we have for the evaluated point. So we have to also compute the arc length. So we know that the s is equal to r4 prime of t dt, magnitude of that. So we find r derivative of r4 of t, and that is going to be equal to, when you differentiate this, we are going to have 1, 0, 0, right? So our r prime of r4 prime of t, the magnitude of that will be equal to 1 squared plus 0 squared plus 0 squared, and that is equal to square root of what? 1, which is basically 1. So the magnitude of the r4, r prime of t, is 1. So now we can integrate from 0 to 1 of -3 plus t. Our ds is now 1 dt, right? So we integrate this, we're going to have -3t plus t squared on 2 from 0 to 1. So we're going to have -3 into 1 plus 1 on 2 plus half is equal to 0.5 minus 3, right? And that is equal to -2.5, right? So the fourth segment is -2.5. Okay, so we have the first segment, we have the second segment, the third segment, and the fourth segment. What we have to do is to sum all, right? So finally, we combine all segments. We're going to have minus 1.414 minus 2.236 minus 6.124 minus 2.5, and that is basically minus 12.27. Right, so the evaluated line integral, where C is the path from this point, is given as minus 12.27. Minus 12.27. So that is question number 7. Now let's move on to question number 8. With question number 8, we want to compute the div of di squared r with respect to the mixed variables dy dx minus di squared r with respect to y squared partially, right? We want to take the magnitude of this thing, right? So first of all, we start with di squared r with respect to di y di x minus di squared r with respect to di y squared, right? So we're going to tackle the mixed partials before we come to this, right? So what I'm going to begin with is the mixed partials. So di squared r with respect to y with respect to x is equal to di squared y into di r di x, right? So first of all, we are going to begin with this, the inside. So we're going to have di r with respect to x equals, so we take it term by term, right? So we begin with the first term. So the I component. So the I component, of which we have s squared sine into xy j, right? So we're going to find di r di x, right? So with respect to x of this function, we're going to have 2x sine into xy plus x squared. With respect to x sine xy, we're going to have y out cos into xy, right? So we're going to have 2x sine into xy plus s squared y cos xy, right? So this is what we have for derivative of this. Now we have to find the second part, this as well. So di r with respect to x of the second part minus y cos into xy, right? So we are differentiating this function with respect to x. So we basically, when we differentiate this with respect to x, that means the first function is going to be 0. So we forget about that. So we maintain this, then we differentiate cos xy. So we differentiate cos, we're going to have negative sign. So this part is going to be plus, right? So we have plus y times y sine into xy. So that is equal to y squared sine into xy. Okay, so we are done with the r dx. So the result that we have here, we are going to now depend on that to differentiate partially with respect to y. So we are going to differentiate this partially with respect to y, then we differentiate this to partially with respect to y. So di with respect to y of 2x sine into xy plus x squared y cos into xy right? So we differentiate these two functions with respect to y. Okay, so we begin here. We are differentiating this function with respect to y. So it means that the first function, we are going to leave it because it is x, right? So we're going to have 2x times, we differentiate sine xy, which is going to be cos into xy. Then we differentiate the inside with respect to y. So it means that x will come out, plus we are going to differentiate this with respect to y. So it means we are going to have x squared cos into xy plus cos xy with respect to y. So we're going to have x squared y times x. Then we have sine into xy. That is negative, right? So we have 2x squared cos into xy plus s squared cos into xy minus s squared y. So that is s cubed y sine into xy. So this is basically what we have. So we can combine this term to have 3s squared cos into xy minus s cubed y sine into xy. Okay, so this is what we have for partial derivative of this function with respect to y. So now let's come to the second term. We differentiate that to with respect to y squared sine into xy, right? So we're going to differentiate this 2y sine into xy plus y squared. Then we differentiate sine xy. So x is going to come out. Then we differentiate sine. We're going to have cos into xy here. So we have 2y sine into xy plus xy squared cos into xy. So this is what we have as well for the second part. Okay, so with respect to the squared r, with respect to the mixed variables y, x, this is what we have, this and that, right? Now let's go on to find this the squared r with respect to the y squared. So we are going to handle the first part. So the I component, which is going to be s squared sine into xy here. So we're going to differentiate this partially with respect to y. So partially with respect to y of x squared sine into xy, we're going to have x squared, differential of sine is cos xy, then it means that x will come out, right? So we're going to have s cubed cos into xy, right? And the second part is going to be, okay, this, we are differentiating it 2 times, right? So the squared y squared of s cubed cos into xy will be equal to, we are differentiating with respect to x. So with respect to y, so we're going to have x to the 4 sine into xy minus, right? So this is what we have for the first part. So we go on to the second part where we have negative y cos into xy. So we differentiate that too with respect to y first time and second time. So with respect to y, we're going to have minus cos into xy plus xy sine into xy. Right, so this is what we have for the first time. We go the second time. We go the second time to have this with respect to y. We're going to have minus x sine into xy then plus xy squared cos into xy. So we're going to have minus x sine into xy plus xy squared cos into xy. Right, so this is what we have for the second part as well. So this is the first part, this is the second part. So we are going to subtract this 2 from this 2, right? So we are going to have okay, so once we have this, all right, of which it is this and that, right? This is the I component and this is the j component of this, and then this is the I component, this is the j component of this. So we're going to substitute, we're going to subtract this from this, then we subtract this from this, right? And we're going to evaluate at the point 1, 0. All right, so we don't need to stress ourselves, right? We have to substitute the point inside to make the work so easy. So we substitute 1, 0 here, then we're going to have 0, because when you substitute 1, you're going to have 1 times sine of 0 is 0. So we have 0 here. When you substitute 1, 0 here, it means you're going to put x in place of 1 in place of x, then we have sine 0 plus 1 into 0 cos into 0, right? And we know that this will give us 0 plus this part will be 0. So this part is gone. Then we come here, we substitute 1 here, we substitute 0 here. So we're going to have 3 cos into 0, of which we know that cos 0 is 1. So we have 3. Then this part, because of the sign, we're going to have 0. So this part too goes to 0. So we have 3i. Then this part as well, because of the sign and because of y, when you substitute the point inside, this part will go to 0. And this part too, because of the y here, when you substitute cos 0, which is 1, times y, which is 0, we're going to have 0 here. So we're going to say that when we evaluated this, we have negative 3i, right? And when you find the magnitude of this, we're going to have square root of negative 3i squared plus 0j squared plus 0k squared, right? So this, we are going to basically have square root of 9 plus 0, and that is equal to 3. So the value of this is basically 3. So if this is equal to that, then when we compute di squared r with respect to the mixed partial yx minus di squared r with respect to di y squared at this point 0 and 1, then we have 3, and that is our answer to question number 8. Okay, so on our question paper is option A. So we have 3. Okay, so let's move on to question number 9. So with question number, okay, so with question number 9, we want to evaluate this line integral, right? 2x minus e to the negative y squared dy plus sine x plus 3y squared dx, where c is the boundary of the half disk x squared plus y squared less than or equal to p squared, and y is greater than or equal to 0. Oriented clockwise, oriented counterclockwise, right? So basically, this question is telling us that this line integral of 2x minus e to the negative y squared dy plus sine x plus 3y squared dx, right? So they are telling us that C is the boundary of the half disk, right? So basically that is the boundary of the upper half disk, where upper half disk x squared plus y squared less than or equal to p squared, where y is greater than or equal to 0. Okay, so what we have to know about this problem is that we are trying to transverse this particular counterclockwise. We have to traverse this counterclockwise, right? So we're going to do that. So we know that step 1, we know that Green's theorem says if a vector field is defined and continuously differentiable over a region, say P, right? Bounded, the region P, which is bounded by positively oriented piecewise smooth, simple, closed curve C, right? Then we can say that, this is just a sketch to illustrate something. So this is y, this is x, and okay, and we have x squared plus y squared less than or equal to p squared, right? Right. Now, once we know that Green's theorem is basically if a vector field is defined and continuously differentiable over a region P, bounded by positively oriented, piecewise, and smooth with simple closed curve, then we can say that our line integral 2x minus e to the negative y squared dy plus sine x plus 3y squared dx, right? So this here we can write it, say that this is m dx plus n dy. Okay, and that is equal to double integral over the region R, no, over the region is P here, right? Over the region P of partial differential of n with respect to x minus partial differential of m with respect to y, odd a, right? So step 2, this is our step 1. Step 2, let's identify our m and our n from this line integral, right? So our m here, our m dx plus n dy here, our m of x and y will be equal to this, right? So that will be sine x plus 3y squared, and our n of x and y will be equal to this 2x minus e to the power negative y squared. So this and this is what we have. If this were to be differential equation, we know that in there, the first part, the term containing the dx becomes our m of x and y, right? The same knowledge we are applying here. In here, this is our m of x and y. This is our n of x and y, right? So we come up here. So we're going to find, so step 3, we're going to find a partial derivative to each of the terms, right? So partial derivative using the Green's theorem, right? So we know that double integral over the boundary, right? P minus the A. So we are going to take them one by one. So partial differential of n with respect to x will be equal to partial of this with respect to n. So where is the n? This is our n. So of 2x minus e to the negative y squared. So when we differentiate this with respect to x, we are going to have 2. We are going to have basically 2, right? This with respect to x, we're going to have 2 because when you differentiate 2x, we're going to have 2 here. Differentiate negative e power negative y squared, because there is no x term, it goes to 0. So we come to the m with respect to y. That will be equal to the, and that is here. So we have sine x plus 3y squared. So with respect to y, sine x goes to 0, and then we differentiate 3y squared, and that becomes 6y. Okay, so once we have the partial with respect to x of n of x and y, and partial with respect to y of m of x and y, respectively, then we can say that the n with respect to x minus the m with respect to y will be equal to 2 minus 6y, right? So step, we have been able to identify this, right? So we can substitute that there now. Okay, so we're going to have a double integral over the boundary into 2 minus 6y dA, right? So how do we get our dA? We know that dA is basically write this double integral in the polar coordinate form. So that will be equal to this over the boundary P into 2 minus 6r sine theta times r d theta dr, right? The r d theta, right? So the r d theta. So this is in the polar coordinate form. So we're going to have r, so 2 minus 6r sine theta multiplied by r dr d theta, right? So let's evaluate the inner integrand, right? So we're going to evaluate the inner integrand first, okay? With respect to, let's evaluate the inner integral, right? So we're going to have this. Let's try to expand this first. So 2r minus 6r squared sine theta dr d theta, right? So let's evaluate the inner integrand first. So this first, then we come to this. So we're going to have p, so from 0 to p of 2r minus 6r squared sine theta dr, right? So we're going to integrate this with respect to r. So when we do that, we're going to have 2r squared over r, 2r squared over 2 minus 6r cubed over 3 sine theta. So from 0 to p, right? So we're going to have r squared minus 2r cubed sine theta from 0 to p. So we're going to substitute that. Then we have p squared minus 2r cubed, 2p cubed sine theta, right? Minus 0 minus 2 into 0 sine theta, right? So basically this part goes to 0. So this is what we have for integrating the inner integrand, right? So we're going to use this to integrate the outer. Okay, so this is what we have for the inner integrand. So we're going to use this to evaluate the outer integrand. So we're going to have from 0 to pi of p squared minus 2p cubed sine theta, right? The theta, right? So from here, we can decide to separate them. So we're going to have from 0 to pi p squared the theta minus from 0 to pi 2p cubed sine theta d theta, right? So we deal with this. When you deal with this, you're going to have, with respect to pi, you're going to have p squared pi from 0 to pi minus this one. We know that minus 2p cubed is a constant, so we bring that out. So from 0 to pi sine theta d theta, right? So here, let's try to substitute the pi inside. So we have pi p squared minus 2p cubed. Integral of sine is negative cos, right? So we have negative cos theta from 0 to pi. Okay, so we're going to have pi squared minus 2 pi cubed into, we know that cos pi is basically 1, negative 1, right? So we're going to have negative, so we're going to have pi p squared minus 2p cubed into 1 plus 1, right? So we have pi p squared minus 2p cubed into 2. So we're going to have pi p squared minus 4p cubed. So this we can factor p squared out. Then we have pi minus 4p. Okay, so this becomes our final solution to this particular problem. All right, and this is option D. Option D, right? So p squared into pi minus 4p is our final answer to question number 9. Okay, let's move on to question number 10. Question number 10, we want to find the mass of a wire lying along the first octant part C of the curve of intersection of the elliptic paraboloid z equals 2 minus x squared minus 2y squared and the parabolic cylinder z equals x squared between 0, 1, 0 and 1, 0, 1. If the density of the wire at position xyz is p of xyz equals xy. Okay, so with this problem, we have been given two surfaces, all right? That is the elliptic paraboloid, z equals 2 minus x squared minus 2y squared. And we have been given the parabolic cylinder, z equals x squared, right? With density p of xyz to be equal to xy. And the wire lies along the curve C formed by the intersection of the two surfaces in the first octant, right? So the first between the two surfaces, so we're going to have this to be 0, 1, 0, then B to be equal to 1, 0, 1. Okay, so first of all, what we have to do is to find the curve of intersection. So set the two expressions for z equals, so we're going to have, this, right? So z equals this and z equals that. So we set them equal. So equate that to that. So we're going to have z squared, x squared equals 2 minus x squared minus 2y squared, right? So when this comes, you're going to have 2x squared equals 2 minus 2y squared. Okay, so when you divide through by 2, you're going to have x squared equals 1 minus y squared, right? So that becomes, so we're going to have x squared plus y squared equals 1. Okay, so this is what we have. So the curve of intersection in the xy plane satisfy x equals 1 minus y squared. In the xy plane satisfies x equals 1 minus y squared, or under the square root sign, right? And we know that z is equal to x squared, and of which it will be equal to 1 minus y squared, right? So now we have to parameterize the curve at 0, 1 inclusive. So meaning that y belongs to 0 and 1 inclusive, right? So from here, we have our point 0, 1, 0, and 0, that is 1, 0, 1, right? So if you want to parameterize that, then we're going to say that x equals square root of 1 minus t squared. When we parameterize this, then we're going to have x equals 1 minus t squared, all under the square root sign. So let me explain how the parameterization is being done. So if you want to get the x coordinate, okay, so now let's parameterize the curve at where y, so let's y, let's y belongs to what? T, of which we have 0, 1 inclusive, right? So if y is t, then means that we are going to have x to be equal to square root of 1 minus t squared. And then we're going to have z equals 1 minus t squared. So now our curve becomes, now our curve becomes this square root of 1 minus t squared. Then our y is t, and our z is 1 minus t squared, right? Okay, so this is what we have for our curve. So once we have the curve, what we have to do is that we have to find the mass of the wire along the curve, right? So this is our curve so far. So we have to find the mass of the wire along this curve, right? So here we're going to say that our mass M is equal to, we are integrating over this limit, right? 0 to 1 of P of X, Y, Z, the X, right? So to get the X, it means that we have to find R prime of T, magnitude of that, the T, right? So we're going to have R prime of T to be equal to, when you differentiate this with respect to T, then we are going to have, this is the same as 1 minus T squared power half, right? So we're going to have half into 1 minus T squared times minus 2, right? So minus 2T. So we're going to have minus 2T over 2 into 1 minus T squared or negative half. So basically, we're going to have minus T over 1 minus T squared under the square root sign. So the first part, so we have our R prime of T to be equal to negative T over square root of 1 minus T squared, comma, we differentiate T, then we have 1. We differentiate 1 minus T squared, we have minus 2T, right? So this is what we have, and we're going to replace, it means we have to find the magnitude of that, right? So we find the magnitude of this, then we're going to have square root of minus T over square root of 1 minus T squared, all squared, plus 1 squared plus minus 2 squared, right? So this will give us T squared over 1 minus T squared plus 1 plus 4T squared, right? So this, when we simplify this, we're going to have T squared plus 1 minus T squared plus 4T squared 1 minus T squared, right? So basically, we're going to have this taken off this. So we have 1 plus 4T squared minus 4T to the 4. Okay, so this is what we have for the magnitude of the R prime of T. Okay, so once we have the magnitude of R prime of T, then what we have to do is to substitute into the integrand, right? So we're going to have our mass to be equal to integral from 0 to 1 of T multiplied by square root of 1 minus T squared times this, right? So that is also 1 plus 4T squared minus 4T to the 4th, right? All divided by 1 minus T squared, right? So this all divided by 1 minus T squared. Okay, so the T. So our mass will be equal to, we can express this as 1 minus T squared times square root of 1 plus 4t squared minus 4t to the fourth divided by square root of 1 minus t squared, right? The t. So this cancels this. So we're going to have integral from 0 to 1 t times square root of 1 plus 4t squared minus 4t to the fourth. Right. So our mass will eventually yield, when you integrate this, we can neither use substitution nor any, I don't know the method to use here to be able to evaluate this. But this, when you punch this numerically, then you're going to have your mass to be equal to pi plus 2 divided by 8. And that is equal to pi over 8 plus 2 over 8. So that is pi over 8 plus 1 on 4. So you can either leave your solution in this form or in this form, right? So we have our mass of the wire lying along the first octant to be equal to pi on 8, pi plus 2 on 8. Okay. So that is the mass of the wire lying along the first octant part, C. Okay, pi plus 2 all divided by 8. Okay, so now let's move on to question number 11. Okay, so with question number 11, we want to find the work done by the force field F equals minus xi plus yj plus zk in moving a particle along the curve r of t equals cos 2ti plus 3tj minus sine 2tk for 0 less than or equal to t less than or equal to pi on 2, right? So this is our expectation. We want to compute the work done by the force field along this curve, right? Along this curve, right? This is the curve. Okay. So we know that work done is equal to this line integral force, that is the force field times the R, right? So it means we need this to be able to deal with this, right? So first of all, we deal that over a particular limit a to b of position vector f times r of t, all right, times r prime of t dt. Okay, so it means that we have to substitute r of t into f, right? You have to substitute r of t into f. Then we dot it with r prime of t. So let's find r prime of t first. So r prime of t will be equal to, we are differentiating this curve, right? So when you differentiate cos, we're going to have negative sign. So we have negative 2 sine 2t I plus, when you differentiate 3tj, you're going to have 3j. Also, when you differentiate sine 2t, there is a negative there. So when you differentiate sine 2t, you're going to have cos. So you're going to have minus 2 cos 2tk. Right. So once we have the differential of the curve along this as this, then we're going to say that f of r of t, we're going to substitute x equals cos s equals cos 2t, y equals 3t, and z equals negative sine into 2t into this f. And we know that our f is equal to negative xi plus yj plus zk, right? So wherever we see x, we substitute cos 2t. So we're going to have our f to be equal to f of r of t to be equal to negative cos 2t I plus our y is 3t. So we have 3tg plus our z is negative sine 2t. Okay, right. So once we have that, then we have to find the dot of this with this, right? So f of r of t dot r prime of t will be equal to this dot this. So we're going to have minus cos 2ti plus 3tj minus sine into 2t k dot this minus 2 sine into 2t I plus 3j minus 2 cos into 2t k, right? So component wise, this to this will give us 2 cos 2t sine 2t. Then this to this, we're going to have plus 9t, right? This to this, we're going to have plus 2 cos 2t sine 2t. Okay, so this and this, we are going to have 4 cos 2t sine 2t. Okay. Four cos 2t sine 2t plus 9. Okay, so this is what we have for this. So it means this is what we are going to integrate, right? So we are going to integrate that. But don't forget that 4 cos 2t sine 2t is equal to 2, is basically equal to sine into 4t, right? So this is an identity of which is equal to sine 4t, right? So now we're going to, this is what we are going to integrate, right? So we say that our f of r of t dot r prime of t is equal to 9 plus sine into 4t, right? So we're going to integrate this now. So we come here, we say that integral from 0 to pi on 2 of sine into 4t plus 9 or dt, right? So that is our work done. So we're going to say that we're going to say that our work done equals 9 plus sine into 4t dt, right? So we can separate them to have this from 0 to pi on 2, 9 dt plus 0 to pi on 2 sine into 4t dt, right? So we integrate this with respect to t, then we are going to have 9t from 0 to pi on 2 plus we integrate sine 4t, then we are going to have negative cos 4t divided by 4 from 0 to pi on 2. So we come down, we substitute the limits, and we're going to have 9 into pi on 2 plus we substitute our work done will be equal to 9 is a constant, so we factor that out from 0 to pi on 2 dt plus from 0 to pi on 2 sine into 4t dt. This will go to 0 because when you integrate that, you're going to have cos. Okay, so we go to work done to be equal to 9 into, when you integrate t, you're going to have t squared on 2 from 0 to pi on 2 plus, when you integrate cos, you're going to have, integrate sine, you're going to have negative cos into 4t divided by 4 from 0 to pi on 2. So this, you're going to have 9 into, we substitute the limits, and we're going to have pi on 2 all squared divided by 2 minus 0, right? So plus, when you substitute pi on 2 here, you're going to have what? Cos 180, and cos 180 is 1. So we're going to have minus 1 on 4, then minus cos 0, and cos 0 is 1. So we're going to have 1 on 4, right? So eventually we're going to have 9 into pi squared on 4 times 2, right? Plus this will give us 0. So we have 0 here. Then we know that our work done will be equal to 9 pi squared times 2 divided by 4. That will be equal to, this to cancel 2 of this. So we have 9 pi squared divided by 2. So we have so we're going to have times 2 here. So this times 2. So we're going to have 9 pi squared divided by 8. So the mass, the work done by the force field is, equal to 9 pi squared divided by 8. Okay, so this is the work done by the force field. So if you want to find the work done by a particular force field, know that work done is giving us from a lower limit to upper limit of the force field into the curve, right? Dot r prime of t. So you just have to substitute r of t into the f, right? Then you dot it with, after finding the derivative of r. So what you need is derivative of r of t, then You substitute r of t into f. Once you are done doing the substitution, then you dot the result that you have with the derivative of r of t. The result you're going to obtain, that is what you are going to integrate over the particular limit. Okay, so now let's move on to question number 12. Okay, so this 9 pi squared over 8 can be expressed as 1.125 pi squared. So our work done by the force field is equal to 1.125 pi squared. Okay, so with question number 12, we want to evaluate this line integral x plus yz dx plus 2x dy plus xyz dz, where C consists of line segment from 1, 0, 0, 1, 0, 1 to 2, 3, 1, and from 2, 3, 1 to 2, 5, 2. Okay, so first of all, we know that we have been given this line integral x plus yz or dx plus 2x dy plus xyz dz, right? And C consists of line segments from this to this and from this to that, right? So it means we have two segments. So we have to parameterize each segment, we evaluate each segment, then we find the arc length. Then we go ahead to integrate each segment, right? So we're going to find, so let's consider this, the first part. So the first part, we're going to consider 1, 0, 1 to 2, 3, 1, right? So we're going to parameterize that. So let's call this A, which is 1, 0, 0, 1, 0, 1, and call this B, 2, 3, 1. So this is how you parameterize it. You know, for the x component, you're going to have x naught plus x1 minus x naught multiplied by a scalar, right? Then, so your x naught here is 1 and your x1 is 2. Okay, so let's substitute to find our x component. So that will be equal to 1 plus 2 minus 1 t. So we have x to be equal to 1 plus 2t minus t. So this is basically equal to 1 plus t. So that is for the x component, 1 plus t. Okay. So we find the y component to be equal to y naught plus y1 minus y naught multiplied by this. So the y naught here is 0. The y1 here is 3. So we have y to be equal to 0 plus 3 minus 0 t. So we have y to be equal to 0 plus 3t. So this is 3t. So that is the second component, and this is the first component. So let's look at the last component, which is the z. So z naught will be equal to 1 and z1 will be equal to 1, right? So we have our z to be equal to z naught plus z1 minus z naught multiplied by t. So we're going to have our z to be equal to 1 plus 1 minus 1 t. So we have z to be 1 plus 0 times t, so we have z to be equal to 1. Okay, so now we have x, we have y to be 3 and z to be 1. So now let's find the x to be equal to what? The t. And then we find the y to be equal to 3 the t. Then we find the z to be equal to what? 0, because z is a constant. So when you find differential of 1, you get what? 0. Okay, so now that we have all that, then we can substitute. We're going to have x plus 2, x plus yz. The x will be equal to, our x now is 1 plus t, plus our y is 3t, and our dx is dt, right? So we have dt. Okay, so that is going to be 1 plus 4t dt for the first part. Then we go to the second part where we have 2x dy. So our x is 1 plus t. So we have 2 into 1 plus t. Dy is 3 dt. So we have 3 dt. So we're going to have 2 plus 2t multiplied by 3 dt. So this, you're going to have 6 plus 6t dt, right? Then we come to the last part, x, y, z, z. So we're going to have x, y, z, dz. And since dz is 0, that means that the whole of this part will go to what? 0. Okay, so now let's evaluate that. So we're going to put in the first integrand, right? So c1 into this, we had this, right? So that is 1 plus 4t dt plus this 6 plus 6t dt, right? So we can separate that. So when you integrate this with respect to t, we're going to have t plus 4t squared divided by 2 plus, when you integrate this, you're going to have 6t plus 6t squared divided by 2. Don't forget, over the limit 0 to 1. 0 to 1. Okay, so this, when you evaluate that, you're going to have 2t squared from 0 to 1 plus 6t plus 3t squared from 0 to 1, right? So this, when you substitute to 1, you're going to have 1 plus 2 into 1 plus 6 plus 3 into 1, right? So we're going to have 1 plus 2 plus 6 plus 3, right? And this is basically 3 plus 9, which is equal to 12. So we have our integral, first integral to be what? 12, right? So that is the first segment. So we come to the second segment where we have 2, 3, 1 to 2, 5, 2, right? So let's name this A and then B, right? So if you want to parameterize this, then means we have to find x, y, z, right? So in doing that, then x will be equal to x naught plus x1 minus x naught t, and our x naught here is 2, our x1 here is 2, right? So we're going to have x equals 2 plus 2 minus 2 t. So our x will be what? 2. Our y will be equal to y naught plus y1 minus y naught t. And from the question, our y naught is 3, our y1 is 5, right? So we're going to have y to be equal to 3 plus 5 minus 3, all the t. So we have y to be 3 plus 2t. So this is y and this is x. So we have to find z. So we have our z to be equal to z naught plus z1 minus z naught, right? And our z naught here is 1 and our z1 is 2, right? So we substitute that. I'm going to have our z to be equal to 1 plus 2 minus 1 t. So we have z to be 1 plus t. So this is our z. So once we have x, y, z, then it means we have to find derivative of them, right? So since x is what? A constant, it means that our dx will be equal to what? 0. Our dy here is going to be 2 dt, and our dz will be equal to 1 dt, right? So we're going to substitute that information. So let's evaluate. So x plus yz dx, right? So our x is 2. So we have 2 plus y is 3 plus 2t, and our z is 1 plus t, 1 plus t, and our dx is 0. So the whole of this goes to 0, and we only have 2 for this part. So we have that. And then 2x dy. Our x is 2. So we're going to have 4. And our dy is 2 dt. So we're going to have times 2 dt. So that is 8 dt. So we have 2x dy to be equal to 8 dt. Okay, now let's come to the last part, where we have x, y, z, dz. Right, so we know that our x is 2, our y is 3 plus 2t, our z is 1 plus t, and our dz is dt, right? So we're going to have 2 into 3 plus 3t plus 2t plus 2t squared dt. Then I'm going to have 2 into this and this will be 5t. So we have 3 plus 5t plus 2t squared dt. So we expand this, we're going to have 6 plus 10t plus 4t squared dt. Okay, so once we have the last part, we have the second part, and we have the first part to be 0, that means that our second integral is going to be 0 plus 2x dy is 8 dt plus this one is 6 plus 10t plus 4t squared dt, right? So we're going to integrate that. So you know that this is 0, right? So integrate 0 with respect to t plus integrate 8 with respect to t plus integrate 6 plus 10t plus 4t squared dt. We're going to integrate this term by term. So when we do that, we integrate 8 dt from 0 to 1. We're going to have 8t from 0 to 1, and that will be equal to 8 into 1, and that is basically 8. So we have 8 for this part. Let's take integral of 6 plus 10t plus 4t squared dt, right? So integrate 6, we integrate that, we're going to have 6t plus 10t squared over 2 plus 4t cubed over 3 from 0 to 1. Okay, so we're going to have 6t plus 5t squared plus 4 on 3 t cubed from 0 to 1. So we're going to substitute the limits now. So we're going to have 6 into 1 plus 5 into 1 squared plus 4 on 3 into 1 cube, right? So we're going to have 6 plus 5 plus 4 on 3, 4 on 3. So this and this will give us 11 plus this and this will be 11. 11 plus 4 on 3 is basically 12.333. All right, so now that we have this, the integral of this, that, and that, so we're going to add also a first integral plus second integral. So that is going to be 12 plus 8 plus 12.333, and that is equal to 32.333. Okay, so that is the value to this particular problem. So we evaluated this and we have 32.33 for question number 12. Okay, now let's move on to question number 13. With question number 13, we want to use the Green's theorem to evaluate this line integral, where C is the region bounded by y squared equals x and x squared equals y. Okay, so what does the Green's theorem does? So basically the Green's theorem, it converts line integral around a closed, around a simple closed curve, say C, right, into a double integral over the region that it has been given. So over the region R. Okay, so it encloses that. So that is basically the Green's theorem, what it does. Okay, so basically we're going to have that is giving us this of p dx minus q dy, right? So that is the green. Now that we know this, then we have to write the double integral over the region R of partial derivative of q with respect to x minus partial derivative of p with respect to y, or the a, right? And our p here is 5xy plus x squared, and our q is 2 minus x squared y squared, right? So we're going to take partial derivative with respect to y of p. So partial derivative with respect to y of p is going to be 5x, 5x. Then partial derivative of q with respect to x will be equal to minus 2x y squared. Okay, so when you take this from this, then you're going to have the q with respect to x minus the p with respect to y, and that is equal to minus 2x y squared minus 5x, right? So that is what we are going to substitute here, right? So we're going to have a double integral of minus 2x y squared minus 5x dA, right? So this is what we have. Now, once we have this, then it means, don't forget that once we have this, then we have to determine the region bounded by this, right? And we are told that C is the region bounded by y squared equals x. And this alone is not a closed region, right? We need both an upper and lower curve, right? So we see that y equals x squared, of which is basically a parabola. A parabola opening upwards, So the inverse is going to be y equals square root of x. That is the inverse. So of x squared equals y. So the inverse of x squared equals y is y equals square root of x. So the bounded region is between y equals x squared and y equals square root of x. So we assume this, right? This parabola opening upward, because this alone is not a closed curve. This alone is not a closed curve, right? But this, we know that this is exactly what we need. So this one is not a closed curve. So we make sure that it's a closed curve by changing this to a parabola, which is y equals x squared, right? So from here, now our double integral is giving us minus 2xy y squared minus 5x dA, and we know that it is bounded below x squared and above square root of x, right? So we're going to have our double integral to be, so this is in a region of 0 and 1, right? So from 0 to 1 of the second part is x squared to square root of x. So that is y equals x squared and y equals square root of x of minus 2xy squared minus 5x dA. Don't forget that this is dy dx. So we're going to have this to be equal to of minus 2xy squared minus 5x dy dx, right? So now that we've set up our double integral, then we know that we integrate the inner integrand first. So we're going to integrate this first with respect to y. So from y equals square root of y equals x squared to y equals square root of x of negative 2x y squared minus 5x dy, right? So this we can factor out x. So we're going to have x squared, x square root of x minus x into 2y squared minus plus 5 dy. Don't forget we are integrating with respect to y, so this becomes a constant, so we can factor that out. Right? So when we integrate this with respect to y, then we're going to have 2y cubed over 3 plus 5y from x squared to square root of x. So we're going to substitute this limit, then we're going to have minus x into 2 on 3 into square root of x cubed plus 5 into square root of x minus 2 over 3 into x squared cubed plus 5 into x squared. Okay, so this is what we have. So we can say that this minus x into 2 over 3 times x to the power half times 3 plus 5x to the power half, right? Minus 2 over 3 x to the power 6 plus 5x to the power 2, right? So we're going to have minus x into 2 over 3 x to the power 3 on 2 plus 5x to the power half minus 2 over 3 x to the power 6 plus 5x to the power 2, right? So we expand that, we're going to have minus 2 over 3 x to the power 2 on 3, 3 on 2 plus 1 is basically 5 on 2, right? So 5 on 2 plus half plus, so we're going to have 5x to the power 3 on 2 minus 2 on 3 x to the power 7 plus 5. So that's going to be minus. So minus 5x to the power 3. So this is what we have. This is what we are going to integrate the second time with respect to x. So we are going to integrate that with respect to x. So from 0 to 1 of minus 2 on 3 x to the 5 on 2 plus 5x to the 3 on 2 minus 2 on 3 x to the 7 minus 5x to the 3 here. Okay, so we integrate this, then evaluate at this limit. So we're going to have integral of minus 2 x to the power 5 on 2 is going to be 7 on 2 divided by this. So going to be 2 over 7, right? Plus 5x to the power 5 on 2 times 2 on 5 minus minus 2 on 3 x to the power 8 times 8 minus 5x to the power 4 times over 4, right? So this is basically over 24. Okay, so from 0 to 1. So when we evaluate that, we're going to have minus 2 on minus 4 on 21 x to the 7 on 2 plus 2x to the 5 on 2 minus 2 on 24 x to the 8 minus 5 on 4 x to the 4 from 0 to 1, right? So we're going to have minus 4 over 21 into 1 minus 2 into 1 minus, so that is going to be plus 1 on 12 minus 5 on 4 into 1. So we evaluate this, we're going to have minus 4 on 21 minus 2 plus 1 on 12 minus 4 on 4, 5 on 4, and that is basically minus 6 on 7. Okay, so with question number 13, you're going to have minus 6 on 7. By evaluating this line integral, 2 minus x squared y squared dy plus 5xy plus s squared dx, where C is a region bounded by y squared equals x and s squared equals y. So this, using the Green's theorem, you know that you have to convert your line integral into a simple, your line integral into a double integral, right? So once you do that, then you check the region. It has to be bounded below and above, right? And we're given all the necessary information. So this, you know that this alone is not enough, right? So we have to know that y equals x squared is a parabola, right? So we use this instead of that. Then we come here, x squared equals y is basically equal to y squared. Y equals what? Y squared equals square root of y equals square root of what? X. Okay, so once we know this, then this becomes our upper bound and this becomes our lower bound. So we do that substitution, then we'll know what the result will be. So at the end of the problem, we have our answer to be minus 6 over 7. Now let's continue with question number. Okay, so with question number 14, we want to evaluate this integrand, right? And from this integrand, okay, we can see that if we say that 1 minus x equals 0 and x equals 1, we can say that at x equals 1, this function is what? Discontinuous, right? This function is discontinuous at x equals 1 because when you put 1 here, you're going to have 1 minus 1, which is 0. And 1 over 0 will be what? Undefined. So it makes this function discontinuous. But once it is discontinuous, it means we can split it into two parts and check if it converges or it diverges. But when we split this into two parts, we're going to have minus 7 to 1. Because it's discontinuous at x equals 1, our upper limit will be what? 1 of the function x minus 1 minus x to the 2/3 the x plus 1 to 2, right? Of 1 minus x to the 3, right? So this is what we split into 2. So realize that if you take this and you evaluate from a very small number, from 0 to a very small number, say epsilon, right? We know that epsilon is just a number greater than 0. So epsilon greater than 0, right? So if we do that, we're going to say that 1 minus x, right? And we let 1 minus x equals u. So when we substitute here, we're going to say that 1 over u dx, right? And this, we can say that this behaves like this, right? So this is finite at x equals 1. This is finite at x equals 1, and it converges, right? So since it converges, then since this one converges, then it means that both functions will converge. Both integral will converge. So we can use change of limits to solve this, right? So when we apply the change of limits, then we can solve this integral, right? So we're going to say that from -7 to 1 over 1 minus x to third the x, right? So we let u equals 1 minus x. So we see that the u is equal to the x. So from here, we see that if x equals 1, x equals the first limit, -7, then we're going to have u equals 1 minus 7, and that is what? 8. And also, if x equals 2, then we're going to have u equals 1 minus 2. So we have u equals -1. Okay, so this is our new limit. This is our new limit. So we're going to say that from -1 to 8, right? 1 over u du, right? So we're going to have, right? So from here we have -2 to the 3, from -1 to 8, right? So we integrate this, we're going to have -2 over 3 plus 1, right? From -1 to 8, and that is going to give us 1 over u to the power 1 over 3, then divided by 1 over 3 from -1 to 8, right? So we're going to have 3 u to the 1 over 3, -1 to 8. From here, we're going to have 3 into 8 to the power 1 over 3 minus 3 into -1 to the power 1 over 3. And this is basically going to give us 3 into 2 minus 3 into -1, right? So we have 6 plus 3, and that is 9. So our answer to this particular problem is 9, right? Our answer to this particular integration is 9. But initially, this is an improper integration or improper integral, because if you set 1 minus x to 0, you realize that you'll be having discontinuity at x equals 1, right? And if it is discontinuous, it doesn't mean it diverges, right? So you split that particular integrand into 2 parts. Then you check whether it converges or it diverges. If it diverges, then you can go ahead and solve the problem, right? So when we solved it, we had 9. So that is the solution to question number 14. With question number 15, we want to find the area A that is bounded by C, that we have been given this area, right? And they said if C is a smooth closed curve described as this equation, right? And from here, we have to identify the equation. So we can see that x minus 1 plus 2 into y plus 2 all squared equals what? 2. This equation is basically we can express it in the elliptic form, right? The standard elliptic form. So we know that the standard elliptic equation is x squared over a squared plus y squared over b squared equals 1, right? So we can express this in this standard form, right? So we come up x minus 1 all squared plus 2 into y plus 2 over 2, right? So we divide here by 2, divide here by 2, divide here by 2. So this cancels this and this cancels this. So we're going to have x minus 1 all squared divided by 2 plus y plus 2 all squared divided by 1, and that is equal to 1, right? So we can see that this equation is in the form of this, right? So we can say that our a squared is equal to 2, and our a will be equal to square root of 2. The same as we can say that our b is equal to 1, right? Is b squared is equal to 1. So basically b is equal to square root of 1, of which is basically 1, right? And the area bounded by c is that a is equal to this. You know, this is basically in the form of the Green's theorem, right? So we know that this half minus y dx, right? Okay, so the area that is for an ellipse, the area is given as pi a b. For an ellipse, the area is given as this, right? So we see that the area will be equal to pi times square root of 2 times 1. So basically, our area is equal to square root of 2 times pi. And that becomes the area A that is bounded by C, given that A is equal to this, right? So the most crucial thing here is to identify the kind of equation this equation is, right? So realize that this is in the elliptic form, and the area for an elliptic equation, or the area for an elliptic is pi ab, right? And we've identified our a as this and our b as this. So we just substitute and we have this. So that becomes our area, square root of 2 pi. Or you can as well say that pi square root of 2. They are all the same. Okay, so that is question number 15. Now let's move on to question number 16. With question number 16, we want to use the Green's theorem to evaluate this line integral, right? Where C is the counterclockwise boundary of the trapezoid with vertices 0 to -2, 1 to -1, 1, 1, and 0 and 2. All right, so these are our vertices. So these vertices will help us to get the upper and lower limits of the integral, right? So from here, we know that the Green's theorem, let's first state our x sine y squared minus y squared dx plus s squared y cos into y squared plus 3x dy. Okay, so we identify our P and our Q. So from here, we know that partial dq with respect to x minus partial dp with respect to y dA. And this is that is basically what helps us to solve this, because that is how the Green's theorem is being done. It helps us to convert a line integral into a double integral, right? So from here, we know that our P our P of x and y is equal to x sine y squared minus y squared, and our Q of x and y is equal to x squared y cos into y squared plus 3x. Okay, so meaning we have to differentiate this partially with respect to y and differentiate this partially with respect to x. So we're going to say that partial differential of Q with respect to x will be equal to, we are differentiating this partially with respect to x. So we're going to have 2x y squared cos into y squared. So since we are differentiating partially with respect to y with respect to x, that means that we are only going to handle only this. Then we come to this point. So plus 3, differential of 3x with respect to x is 3. Then we come to partial differential of p with respect to y, and that will be equal to, so we are differentiating this with respect to y. So we're going to have 2y x cos into y squared minus 2y. Okay, so this becomes our partial differential of p with respect to y, and this also partial differential of k with respect to x. Okay, so once we have the partials, then we're going to take this from this. So when you take this from this will go to 0, right? So we're going to have partial dp dq with respect to x minus partial dp with respect to y equals 2xy cos into y squared plus 3 minus 2y x or 2xy cos into y squared minus 2y, right? So you can see that when we expand, we're going to have 2xy cos into y squared plus 3 minus 2xy cos y squared plus 2y. So this basically takes off this, and we're going to have 3 plus 2y. Right, so this is the function that we are going to integrate, right? So now that we have our function, let's find the limit, right? The limit we'll be getting the limit from here. So from this, we can see that 0, neg 2 to 1, neg 1, left and right, right? So left and right, so we're going to say that s equals 0 to x equals 1, right? So basically, we're going to have bottom edge, bottom edge line 0, neg 2 to 1, neg 1, right? And that is basically y equals x minus 2. right? Y equals x minus 2 from here. Okay, now that we have that, then we come to top edge line. Okay, so that is also going to be this and that. So that will be 0, 2, 2, 1, 1. So we're going to have y equals negative x plus 2. Okay, so this and this becomes our limits. Once we have our limit, then we can say that, we are just trying to find the limit for y. So we say that y goes from this x minus 2 to minus x plus 2, right? So that is the limit for y. So let's set up our double integral. So our double integral is going to be from 0 to 1, then x minus 2 to negative x plus 2 of the function dA, right? So from 0 to 1, dy dx, right? So we're going to integrate the inner function first. So we take this to integrate. So inner function first. When we are done, then we use the function to integrate outer integrand, right? So we tackle this from this to that, 3 plus 2y dy, right? So we integrate that, we're going to have 3y plus 2y squared from x minus 2 to minus x plus 2, right? So let's handle it one by one, right? So we take the upper limit. So 3 into minus x plus 2 plus minus x plus 2 all squared. That is the upper limit. Let's finish with that. Then we come and take the lower limit and subtract. So we're going to have 3x minus 3x plus 6 plus x squared minus 4x plus 4, right? So this we're going to have x squared. This and this will be minus 7x. This and this will be plus 10. So we have the upper limits. Now let's take the lower limit. 3y plus y squared. We're going to substitute x minus 2. So plus x minus 2 all squared. So we're going to have 3x minus 6 plus x squared minus 4x plus 4. Okay, so this we're going to have x squared this and this will be minus x. This and this will be plus 1, minus 2, right? So now we're going to subtract this from this, right? So we're going to have x squared minus 7x plus 10 minus into x squared minus x minus 2, right? So we have x squared minus 7x plus 10 minus x squared plus x plus 2. So this cancels this and this becomes minus 6x. This and this becomes plus 12. So this is the new function that we are going to integrate with respect to x. So from 0 to 1 of negative 6x plus 12 dx. So from here, we're going to have minus 6x squared divided by 3 divided by 2 plus 2 12x from 0 to 1. Okay, so we're going to have minus 3x squared plus 12x from 0 to 1. So we substitute the limits. We're going to have minus 3 into 1 squared plus 12 into 1. All right? And you know that if you substitute 0, everything will go to 0. So we're going to have only this 3 plus 12, and that is basically 9. Okay, so after evaluating this, we had 9. So our solution to question number 16 is 9, right? That is, if you use Green's theorem to evaluate x sine y squared minus y squared dx plus x squared y cos y squared plus 3x dy, where c is the counterclockwise boundary of the trapezoid with vertices 0, neg 2, 1, neg 1, 1, 1, and 0, 2, you have 9. Okay, so that is option C. That's option C. All right, so question number 17. With question number 17, we want to evaluate this line integral where f of x, y, z is equal to this function and our position vector is this. So now we're going to say that our f of r of t dot r prime of t is what we are going to look for, right? From a limit, lower limit to upper limit. And we know that our limit is, right, say a is equal to 0, b is equal to 1, right? So we're going to find f of r of t dot r prime of t, then we integrate. So we know that from r of t, our x is equal to cos into 2 pi, our y is equal to sine into 2 pi t, and our z is equal to 5t. You know that each component, the first component, the I component is your x, the y component is the j component is your y, and your k component is your z. Okay, so we're going to substitute that into the f. So that will be equal to, when we substitute x here, we're going to have 2 into cos 2 pi t I plus 2z. Our z is 5t, right? 5t. Then plus y. Our y is sine 2 pi t minus z. Z is 5t, or k, right? So let's simplify that. We simplify that, and we're going to have 2 cos into 2 pi t I plus 10 tj. Then we're going to have plus sine 2 pi t minus 5t, or k. Okay, so now we have our f of r of t. We have to find r prime of t. So r prime of t is equal to, we're going to differentiate our r of t. So when you differentiate cos, you have negative sign, and we have 2 pi t inside. It's going to be minus 2 pi sine into 2 pi t I. Then differentiate sine, we're going to have plus 2 pi cos into 2 pi t j. And then we differentiate 5tk, we're going to have plus 5k. Okay, so we're going to dot this with this, right? So we're going to have f of r of t dot r prime of t to be equal to, this is 2 cos 2 pi t I plus 10tj plus sine into 2 pi t minus 5t all k, right? So this times this, which is minus 2 pi sine into 2 pi t I plus 2 pi cos into 2 pi t j plus 5k, right? So we're going to dot this with that. Okay, and you know that I component goes for I components, right? So we're going to have this to this. We're going to have minus 4 pi cos into 2 pi t sine into 2 pi t, right? Then this 10tj times 2 pi cos 2j is going to be 20 pi t cos into 2 pi t. Then this whole of this times this. So we're going to have plus 5 into sine into 2 pi t minus 5t. Okay, so we expand that, and we're going to have minus 4 pi cos into 2 pi t sine into 2 pi t plus 20 pi t cos into 2 pi t plus 5 sine into 2 pi t minus 25t, right? So this is what we have. Can we still simplify this? We have 4 pi cos 2 pi t sine 2 pi t plus, right, okay. Let's integrate, right? But we can break them into parts to integrate. So let's pick this, then we come and pick this, then we pick this, then we pick this, right? So we're going to break it into 1, 2, 3, 4 parts. Okay, so we begin with this from 0 to 1 of minus 4 pi cos into 2 pi t sine into 2 pi t dt, right? So we know that this is a constant, so we factor that out. From 0 to 1 cos into 2 pi t sine into 2 pi t dt, right? This we have to use an identity. Remember that if you have sine into 2a is the same as 2 sine A cos A, right? So basically we can say that cos 2 pi t sine 2 pi t is equal to 1 over 2 sine 4 pi t. Okay, so we're going to substitute this with this, right? So that is an identity. So minus 4 pi integral from 0 to 1 of half sine 4 pi t dt. Okay, so from here, we're going to say that minus 4 pi from 0 to 1 of half sine into 4 pi t dt, right? So we factor the half out. I'm going to have minus 2 pi from 0 to 1 sine into 4 pi t dt, right? So this, we integrate this, right? So we integrate sine 4 pi t, we're going to have minus 2 pi out, right? You integrate this, you're going to have negative cos into 4 pi t divided by 4 pi from 0 to 1, right? Then we can factor the 1 over 4 pi out and do that from negative. From here, we know that cos 4 pi is 1. So we're going to have minus half out, minus into 1 plus 1, right? So this, we're going to have minus half into minus 1 plus 1. And this is basically half minus half into what? 0. So that is giving us 0. So that portion is giving us 0. So this part is 0. Okay, so we have to go to the next part. It means the first term is not necessary. So we come to this part where we have integral from 0 to 1, 20 pi t cos into 2 pi t dt, right? So we factor the 20 pi out, and we're going to have t cos 2 pi t dt. When you integrate this, you know that this we have to use by parts, right? We have to use by parts here. And this, we can use the DI method, right? So with the DI method, we're going to have our t here. Then we have our cos 2 pi t here, right? So we differentiate this, we have 1. We differentiate again, we have 0. Then we come here, we integrate, right? So we integrate cos 2 pi t, you're going to have sine 2 pi t divided by 2 pi, right? Then you integrate again, you're going to have negative cos 2 pi t divided by 4 pi squared. Okay, so this is what we have. So this goes to this goes to that, plus, minus. Okay, so we're going to say that this to that, we're going to have t sine 2 pi t divided by 2 pi. Then this to this, we're going to have minus cos 2 pi t divided by 4 pi squared. Right, so this is what we have for the second term. So we're going to integrate this over the limit. So right, we've integrated this. So we're going to have from minus cos 2 pi t divided by 5 pi squared, right? So from here, we substitute the limits. So 1 here, we're going to have 1 sine into 2 pi divided by 2 pi minus cos into 2 pi divided by 4 pi squared minus, because of the 0, this part will go to 0. Then cos 0 is 1. So we're going to have minus minus 1 over 4 pi squared, right? This will go to 0, and this as well. This will go to 0, and this part will become minus 1 over 4 pi squared plus 1 over 4 pi squared. So that gives us 0. So it means that the second term, 20 pi t cos 2 pi t, also give us 0. So now we go on to the next term, of which is going to be this. So we're going to integrate from 0 to 1 of 5 sine 2 pi t dt, right? So 5 out from 0 to 1 sine 2 pi t dt. So we integrate this, we're going to have negative cos into 2 pi t divided by 2 pi from 0 to 1, right? I know that when you substitute 1 here, we're going to have 5 cos 180 is 1, and this one too is going to is minus 1, right? So this part is minus 1, and this part is also plus 1, right? So it's going to give us 0. So it means that the third part also give us 0. So we move to minus 25t. So we're going to deal with minus 25t, right? So we integrate from 0 to 1 minus 25t dt, right? So we have minus 25 from 0 to 1 t dt, right? So we integrate that, we have t squared over 2 from 0 to 1. That will be equal to minus 25 into 1 and 2. So that is going to be minus 25 over 2, which is equal to minus 12.5. So we have this part, we have minus 12.5. Now we go to the last part, which is sine squared 2 pi t. So we're going to integrate 0 to 1 sine squared 2 pi t dt, right? So we're going to integrate this to have, no, we can't integrate this straightforward. We have to introduce an identity, right? So we know that sine squared 2t will be equal to 1 minus cos squared cos 2t divided by 2. So we're going to substitute this in place of this, right? So from 0 to 1, 1 minus cos into 2 pi t divided by 2 dt. So we can take half out. From 0 to 1, 1 minus cos 2t dt. So we're going to integrate 1, then we have t, minus sine into 2 pi t divided by 2 pi, right? From 0 to 1 of this. Okay, so we're going to have, so we deal with this as well. So we're going to have this out. So 2 pi out from 0 to 1 sine squared 2 pi t dt. And we know that this, we can use an identity because we can't integrate this straightforward. So we know that sine squared 2 pi is equal to 1 minus cos into 2 pi divided by t divided by 2, right? So we're going to have 2 pi from 0 to 1, 1 minus cos into 2 pi divided by 2 dt, right? So from here, we're going to have 2 pi out times 1 over 2 from 0 to 1, 1 minus cos into 2 pi t dt, right? So we integrate that, we're going to have pi out 0 to 1, 1 minus cos into 2 pi t dt. So we have pi into t minus cos. We integrate cos and we have sine. So we have sine 2 pi t dt, right? 2 sine 2 pi from 0 to 1. So we have pi into, we substitute 1 here, we have 1. 1 minus, we know that 1 minus sine 180 is 0, right? So we have 0 here. And when you substitute 0 here, you're going to have 0. When you substitute 0 into sine, you're going to have 0. So the second, the lower limit goes to 0. So we're going to have pi as our answer. So pi to this, right? So we're going to combine the two to have pi minus 12.5 or pi minus 25 over 2, right? So this is the same as this is the same as 2 pi minus 25 divided by 2, right? So this is the same as 2 pi divided 2 pi minus 25 over 2. Okay, so that is question number 17. That is the process that you go through to get your final answer for question number 17. So our final answer is 2 pi minus 25 divided by 2. Okay, so with question number 18, we want to find, or we want to solve this integrand, right? So first of all, let's simplify the function here. So we know that cube root of 3 into 2 plus 2x, we can express what is under the cube root to have 1 plus x squared times 4. So basically 2 plus 2x squared is equal to 4 into 1 plus x squared. So we are going to substitute this here to have this equals cube root of 3 into 4, 1 plus x squared. Okay, so basically we are going to use that in place of that. So we have from this negative 1 to 3, 1 over cube root of 4 into 1 plus x all squared, right? So basically we've not changed anything, right? We just express what is the terms here to this, right? So that we can have it easy to work with it. So this is from, we're going to have 4 into 1 plus x all to the power 1 over 3, right? So we spread the 1 over 3 to this power and to this as well. So we're going to have 1 over 4 to the power 1 over 3 times 1 plus x to the power 2 over 3, right? So this is what we have so far. So we are going to factor this constant out. So when we do that, we're going to have 1 over 4 to the power 1 over 3 from negative 1 to 3, 1 over 1 plus x to the power 2 over 3. Okay, so this here, we can use substitution, right, to handle this. So the x. Okay, so let's come up here. So we're going to say that we have 1 over 4 to the power 1 over 3 integrate from 1 over 1 plus x to the power 2 over 3 dx. So we are going to say that let u equals 1 plus x, right? So if that is true, then we can have du equals the x, right? So once we've changed this to, we are changing this to du, that means that we have to change the limit as well. So changing of limit or change of limit, right? So if x is equal to negative 1, then u will be equal to 1 plus negative 1. So we're going to have u equals 0. That is for this. Then if x equals 3, the upper limit, then u will be equal to 1 plus 3. So we're going to have 4. Okay, so we are going to use this new limit to evaluate this. So we have 1 over 4 to the power 1 over 3 from this to this, right? That is our new limit now. Then 1 over, now this is u. So we have u to the power 2 over 3. And the s now is the u. So we have du. Okay, so this we can take this up so that the exponent becomes negative. So we have 1 over 4 to the power 1 over 3 integrate from 0 to 4 u to the power negative 2 on 3 du. Now we can easily integrate this, right? So we say that 1 over 4 to the power 1 over 3 integrate this. We're going to have u to the power negative 2 over 3 plus 1, right? From 0 to 4. Okay. This divided by negative 2 over 3 plus 1. And we know that negative 2 over 3 plus 1 is the same as 3, this, right? So we're going to have 1 over 3. Okay, so here you can see that this is equal to 1 over 4 to the power 1 over 3 into u to the power 1 over 3 divided by 1 over 3 from 0 to 4, right? So from here, we can say that we have 1 over 4 to the power 1 over 3 times 3u to the power 1 over 3 from 0 to 4 here. So when we substitute this, the limit, we're going to have, so let's raise this to the power negative 1 over 3, right? So that we have times 3 into 4 to the power 1 over 3 minus 3 into 0 to the power 1 over 3. So we're going to have this into this here. We're going to have 4 to the power 1 over 3 here. Okay, so this is what we have so far. So we can see that this is the same as 3 times 4 to the power 1 over 3 divided by 4 to the power 1 over 3. So this will cancel this so that we have our final answer to be positive 3. So this becomes our solution to this particular problem. So this is equal to 3. Are we good with that? So it's very easy. You know, just to make the work easy, we change this expression from this complex, this to a very simple term. So we change this 2x all squared to this term, right? So that when we are differentiating, it will be much easier for us. So we change this to this and we substituted, right? And we followed the process throughout and we had our final answer to be 3. Okay, so that is option B. That is option B. Now let's move on to question number 19. Okay, so with question number 19, we want to find the potential associated to F for which it is what? Divergence free. And we've been given a hint that G2 is 0. Okay, so this is the vector field, right? F. Okay, so you have been given this vector field F equals 4x plus 13y plus 4z 4i plus 10x minus 2y plus z or j minus into minus 4x minus y plus 2z or k, right? So first of all, we have to determine whether this particular vector field is conservative, right? So that is, if this is conservative, then it means that we have equals 0. So if it is conservative, this must what? Work. Okay. Or we can also say that F, vector field F should be equal to this. Okay. So either this or that, if it is conservative. All right. So, but the question went ahead to tell us that we should find the potential associated to this F, right? For which it is divergence free. Okay, so, and it has given us a hint that G2 is 0. So if G2 is 0, then we can say this is suggesting that if G2 is 0, then this information is suggesting that we are transforming F into another vector field G, right? So such that we are transforming F into another vector field such that F is equal to this times G, right? So this is what we are going to do. So that F is what? So that F is divergence free. That's, this is equal to 0. Okay. So this is expressed as a curl of another vector field, right? So we have to verify F if it is divergence free. So let's say that this cross this, right? Okay, so this cross this dot F is equal to partial differential of the first term with respect to x. So let's say that the first term is f1, then plus partial differential of the second term plus partial differential of the third term, right? First term with respect to x, second term with respect to y, and third term with respect to z. So we can identify our terms here. So f1 is equal to 4x plus 13y plus 4z. So if you differentiate that partially with respect to x, you're going to have this to be equal to 4. Okay, so we have that to be 4, right? We are differentiating with respect to x, so that is what? 4. And then we differentiate the second term, which is this, f2 equals 10x minus 2y plus z with respect to y. So we're going to have this goes to 0, then we're going to have minus 2. This also goes to 0. Then the last term, which is the z. So we have f3 equals negative into negative 4x minus y plus 2z, right? So we differentiate this with respect to z, right? So this expands this, we have plus 4x, but we are differentiating with respect to z. So this goes to 0, this also goes to 0, then we are going to have minus 2. Okay, so this clearly says that this to this is what? Minus 4. Minus 4 plus 4 is 0. So it clearly shows that this is divergence free. So since it is divergence free, as the question says, then we can go ahead and work our problem, right? It's divergence free as the question says. Okay, so the question says that is divergence free, and we've verified for that. Okay, so let's say that f is equal to this position, right? As we said here. Okay, so from here, we're going to say that we are looking at the curve, right? So we're going to have I, J, K. Then this with respect to X, this with respect to Y, and this with respect to Z. Then we have J1, J2, J3, right? So we're going to say that I into D with respect to Y, J2, D with respect to the Z, J3, minus J into with respect to X, J1 with respect to the Z, J3 plus K into with respect to X, J1 with respect to Y, J2, right? So from here, we can say that this to this, so we have partial differential of J3 minus partial differential of J2 with respect to Z. That is the I. Then we come here. So this is basically minus J into partial differential of z with respect to partial differential of J3 with respect to z with respect to z minus partial differential of y with respect to J2, right? So that is the J section. Then we come to the last part. This we have plus k into partial differential of x of G2 minus partial differential of y of G1, right? So this is the I component, this is the J component, and this is the K component. Now, we are going to compare this with the vector field, which is this, right? So we come here, then we say that partial of J3 with respect to y minus partial of J2 with respect to c should be equal to the first component of the f, which is 4x plus 13y plus 4z. Okay, so we name this equation 1. Then we compare this with this. So it's going to be partial differential of G3 with respect to z minus partial differential of G2 with respect to d with respect to y. This is negative, and that is equal to 10x minus 2y plus z, equation. Okay, so let's try to simplify this before we name it equation 2, because there is negative here, so we multiply through so that this comes here and this goes here. So we're going to have partial differential of J2 with respect to y plus minus partial differential of J3 with respect to z equals 10x minus 2y plus z, and that's equation 2. Then we come to the last component, which is partial differential of G2 with respect to x minus partial differential of G1 with respect to y, and that is equal to the last component is going to be 4x plus y minus 2z, and that is equation 3. Now the question said G2 is equal to 0 as a hint. So it's going to make our work so easy. Here we are not going to assume that this should be 0 or that should be 0. The question said G2 is 0. So we're going to say that from equation 1, since G2 is 0, then we are going to have G partial differential of G3 with respect to y equals this G2 is 0, so this part is going off. So we have 4x plus 13y plus 4z, equation 1. Then we come here to, there is G2 here. So we can say that this part goes to 0. Then we have negative partial G3 with respect to z equals 10x minus 2y plus z. So let's try to avoid this negative here. Okay, so that we're going to have partial of G3 with respect to z equals negative 10x plus 2y minus z, equation 2. Then we come to the last part. That as well, we have partial differential of d2, partial differential of g2, and G2 is 0, right? So we're going to have that part goes to 0. Then we have G1 with respect to y because there is a negative here too. So we're going to multiply through by negative. So we have negative 4x, negative y plus 2z, equation 3. Okay, so since G2 is 0, that is why we eliminated all that involves G. So now we are going to integrate this with respect to y so that we can find G3. Okay, so integrate equation 1 with respect to y so that we have this with respect to y equals 4x plus 13y plus 4z, right? So we integrate both sides. So we move this to this section so that we can have this cancels this. So we have J3 equals, we integrate this with respect to y. So we're going to have 4xy plus 13xy, 13y squared divided by 2 plus 4yz. So that is with respect to y. So now we've obtained G3, right? And we integrated with respect to y. So our constant is going to be h of x and z, right? We have 3 variables and we integrated with respect to y. So it means that the constant is going to be what? H of x and z. Now we have J3, so we can easily get J1, right? So since we have J3, we can easily get J1, right? So now let's try to differentiate this with respect to x, right? Okay, so now we're going to integrate this with respect to z. So we're going to have J1 equals 4yz plus 10xz minus 2y squared divided by 2. So we have y squared, right? No, we are integrating with respect to z. So we have minus 2yz plus half z squared plus h of x and z, right? So this is what we have. Now we come up here. Then, okay, so now that we have ky equals minus 4x minus y, then we integrate this with respect to y to have k of x and y equals minus 4xy. We are integrating, right? Minus 4xy minus y squared divided by 2, right? So this plus a constant of c of x and y. Right, so this is what we have. We are going to use the k component to find the k of x and z, right? So we use the k component, of which is the k component from the k component, right? So we're going to use that to find the k of x and z, right? So we have negative G1 respect to y is equal to 4x plus y minus 2z, right? So let's try to divide through by negative. So we have minus 4x minus y plus 2z. So now, since we have G1, the question says G2 is 0, and we had our J3 to be 4xy plus 13 on 2y squared plus 4zy. Okay, so this is our J3, this is our J2, and this is our J1, right? So now we combine all to have our potential vector field. So now we see that this is equal to 10xz plus 2yz plus half z squared minus 4xy minus y squared divided by 2. And this is the I component. Then plus 0j, because the j component, the j2 is 0. So that means that the j component is 0, plus 4xy plus 13 on 2y squared plus 4zy, and that is the k component, right? So finally, since the j component is 0, then we can see that we have 10xz plus 2yz plus z squared on 2 minus 4xy minus y squared on 2 or I plus 4xy plus 13 on 2y squared plus 4zy, and that is the key component, right? So this is option A on the question paper. That is question number 19. So that is question number 19. That is the process that you go through to find the potential associated to a particular vector field, force field, for which it is divergence free. So don't forget, if the question doesn't state that it is divergence free, then you have to check. Even this we checked, right? So you know that if you want to check divergence free, then you take the first component, differentiate with respect to x, then you take the second component, differentiate with respect to y, and then you take the third component, differentiate with respect to z. If you sum all, it should be giving you 0, and that shows that it is divergence free. Once it is divergence free, then you can go ahead and find the potential associated to F, which is the vector field, right? For which it is what? Divergence free. And they gave J2 to what? 0. So all we are looking for is what? J1 and what? J3. All right, and we have that here. Now let's move on to question number 20. Basically, the question number 20 is the question 3, right? There was a slight error, so I needed to jump it and come to question and solve the continuous ones. Okay, so now let's move to question number 20. Basically, the question number 20 is question number 3, right? But I jumped that because there was a slight error with it. But now the error has been rectified, right? So we are going to solve that as question number 20. So with question number 20, we want to evaluate this line integral where C is the circular helix given by this point, right? This function x equals 2 cos t, y equals sine t, and z equals half t. Now the range is 0 less than or equal to t, less than or equal to pi. Okay, so now given these curves, we know that we have been given 2 cos t and y sine t and z equals half t, right? Now we know that the range is also 0 less than or equal to t, less than or equal to pi. Okay, so what we need is this, right? 3y sine z sine 2z, right? Sine 2z dx. So now how do we find the x? The x is equal to square root of differential of x with respect to t all squared plus differential of t, differential of y with respect to t all squared plus differential of z with respect to t all squared. So we have to find all that. Okay, so differential of x with respect to t will be equal to, this is our x, right? So if you differentiate that with respect to t, then we're going to have minus 2 sine t. Then differential of y with respect to t, you're going to have sine t. Differential of sine t is cos t. And then differential of the z with respect to t will be half. Okay, so we have all that, so we can find the x dt, right? The x dt. Okay, so we have differential of the x with respect to t, differential of y with respect to t, and differential of z with respect to t. So now we can say that our dx is equal to minus 2 cos t minus 2 sine t all squared plus 2 cos t all squared plus half all squared, right? The t. So we have the x to be equal to, this become 4 sine squared t plus 4 cos squared t plus 1 on 4, right? So we have the x to be equal to square root of, we factor 4 out, so we have cos squared t plus sine squared t plus 1 on 4. So we have the x to be equal to, this is an identity. So when you substitute that, of which it is going to be 1, then we're going to have 4 into 1 plus 1 on 4. So we have the x to be equal to square root of 4 plus 1 on 4 dt. So we have the x to be equal to square root of 17 on 4 dt. When you simplify this, you have the x to be equal to square root of 17 on 2 dt. So it means that we have the x to be 17 square root of 17 on 2 dt. So we're going to substitute that into the integrand. So we have 3y sine 2z. Now the x is square root of 17 on 2 dt. But don't forget that since sine t is equal to t, then sine 2t sine 2z is equal to sine t as well. So we're going to say that sine 2z will be equal to this and this, right? So you have sine t. So you combine this to this, we're going to have 3y sine 2z will basically be what? 3 sine t sine t. So you have 3 sine squared t. Yeah, so let's simplify that. So you're going to have integral from 0 to 1, 0 to pi of 3 sine squared t times square root of 17 on 2 dt. So we factor this out. So we're going to have 3 on 2 from 0 to pi of sine squared t dt, right? And we know that if you want to integrate this, then you have to use the identity, right? Now remember that integral from 0 to pi of sine squared t dt is equal to pi on 2, right? So yeah, this is 6 because it's 2 of that. So we're going to have 6 here. Okay. So we're going to have 3 integral 3 times what? Square root of 17 on 2. So we're going to have square root of 17 on 2 times pi on 2, right? So that will be equal to 6. This will take off this 3. So we're going to have 3 square root of 17 divided by 2 pi. Okay, so this becomes our final answer to question number 20. All right, so we have what? 3 on 2 times square root of 17 pi. And that is our final answer to question number 20. It's very simple. You just have to follow the process systematically and you're going to get there. Thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye-bye.